All right, hello and welcome to the stream. So today we are going to look at implementing a PSRAM QSPI controller, which will handle the communication between the Raspberry Pi Pico or RP2040 and the PSRAM, which will contain ROM data for this PicoCart64, the Nintendo 64 Flash card using Raspberry Pi Pico. So just to do a small recap, because it's always nice to sort of know what's going on. So where should we start? Yeah, so I'm currently building a flash card using the Raspberry Pi Pico, and I've been investigating different sort of designs on how to do this in a proper way. So the current PCB, the V1, the version 1, that where I ordered PCBs, it's currently on its way, or like haven't really followed the production, but it's probably midway done now and needs a few more days, and then it will be shipped. That will be sort of very bare bones. It's basically only a Raspberry Pi Pico RP2040 module, a stamp module, connected straight to the Nintendo 64 bus. But in the future, we want to do like a nice flash card with lots of features. And the features started out with, we want to have a Wi-Fi module, we want to have an SD card, and we also want the whole sort of ROM loading to be fast. So we want to load it into RAM instead of having it on a flash. Because when you have, excuse me, when you have NOR flash, you need to erase the flash before you can write it again. So that takes quite a lot of time. So by just having a flash, you're sort of limited by performance that way. And also the read accesses currently go through the external flash, through the Raspberry Pi Pico's internal QSPI SPI Flash controller. And that might be a limiting factor for latency and performance. So that's why we want to explore the idea of using the PSRAM instead. So in the last stream, we explored this sort of design, and we iterated on it and ended up with this, which ended up not being like the optimal solution because it's a little bit convoluted. So in this case, we have one Raspberry Pi Pico connected to the N64 bus. It has its own flash, and then it accesses PSRAM through the second Pico. So the signal goes through this Pico, and then this Pico has the PSRAM connected to it. And that is not really optimal, because then we need to write code that sort of shuffles the data through here, and that costs latency and complexity, which is not good. And also, yeah, the pin count is sort of limited, so we can't really do a lot with this design. And also firmware upgrade is complicated here because we have a flash here, and this Pico cannot really access that flash. We would have to write software, and having software that does update adds the possibility of bricking a device, and that is not good. So we have to do something better. So I went back to the drawing board and thought a little bit, and came up with this. So in this case, we have similar situation, just a little bit different. So here, the first Pico, it has a flash. Yeah, also we learned that the external flash can be maximum 16 megabytes because the RP2040's SPI Flash controller can only handle 3-byte addresses, so up to 16 megabytes, but not more. So with this design, we share pins between Pico 1 and Pico 2 over a QSPI bus. So we have 4 IOs and 1 clock, which are both shared from Pico 1 and Pico 2. And we will have to make sure that only one of these are using the bus at the same time. Otherwise you get a bus conflict and that is no fun. But we can save a lot of pins this way. This way the Pico 1 can access the PSRAM directly and the Pico 2 can access the PSRAM directly. Because the Pico 2 will load data from the SD card or Wi-Fi and write that to the PSRAM. So basically the boot sequence will be like Pico 2 boots up, and I guess you want to have an on-screen menu or something, but eventually the Pico 2 loads a ROM from the SD card, writes it to the PSRAM, and then signals to the Pico 1 that, yep, I'm ready, and then the Pico 1 will reboot the Nintendo 64 and load the ROM. Right, so now we know how that works. Then we have the Wi-Fi module is still connected this way, and we have the firmware upgrade problem. How do we do that in a safe way? So here I thought, well, the Pico 2 can connect directly to the SPI flash. So that will take up 4 pins. And we only need to flash with the SPI mode. We don't need QSPI. So then we only need 4 pins. Yeah, so that is one way to do it. And then on the other side, yeah, we get 4 free IOs. It's not that complex, but we still have like a flash memory on the Pico 1, and a flash on the Pico 2. But then I got some feedback from JTH. Thanks for the follow. Which looks a little bit differently. So here, the Pico 1 has no flash at all, but instead the flash pins are connected onto the same bus as the PSRAM, and then to the Pico 2, which is the whole point. And then we have a chip select. The flash chip select is connected to a GPIO on the Pico 2. What this means is that during boot, Pico 1 can read its external flash from Pico 2. And this way, this way you can have dynamic, somehow you still got Wi-Fi before SD card. Yeah. Do you mean that, so actually I had a couple of different approaches here where I wanted to put the SD card here basically, because now we have a bunch of free pins. So that is one design that I was thinking about. So doing basically like this. That is wrong. Sorry, I mean like this. So this way the SD card goes directly to the Pico 2, and the Wi-Fi module is just a peripheral. And this is actually what I prefer to do, because this way the Pico 2 becomes like the central hub of the whole system, and Pico 2 presents firmware to Pico 1, and Pico 2 can also flash the Wi-Fi module if needed. So for example, you could have like a recovery mode where you flash specific firmware to the Pico 2 using the USB bootloader, and then the Pico 2 can sort of update the Wi-Fi module as well. I suggest that Wi-Fi is optional. Really nice to have, but design works without it. I totally agree. It was just very tempting to have a couple of free IOs, because free IOs is a scarcity, or whatever you call it. They are rare. But yeah, I totally agree. And it will also reduce the complexity, because having the SD card proxied through the Wi-Fi module requires software, which is, complex. So yeah, let's actually change it to this, because I think this is much nicer. Performance-wise, I don't know if SD card in SPI mode is like horribly slow. Maybe it's good enough. Because I don't know. I think it will be a sort of a slowish system, however we do it. Or actually not, because let's just think here. So when the Pico 2 wants to load ROM, it will load it from the SD card and write it to the PSRAM. And the PSRAM is very fast. So actually, if we run the SD card in SPI mode, maybe it will be IO bound here instead of somewhere else. But yeah, I totally agree that we should change it like this because this reduces the complexity. But the issue now is that we're low on IOs again. I was thinking, yeah, I don't know if we can share this bus with the SD card. It's kind of scary to do. More testing required. But ditching SD mode unless really hard pressed makes no sense. No. I don't want to ditch SD card. Or what do you mean with SD mode? Is that not the SPI mode? I'm not familiar with the SD cards at all. I have only connected them. Is SD mode when you use all of the IOs at the same time? Because if we want to use all of the pins, then we need 7 IOs, or like 6 plus like this one is. I guess the detection is optional. Like we can just assume all pins. Yes, okay. So in that case, we need 6 pins at least. It's the 4 IOs plus clock 5, and then this one. So 6 pins. So how can we make that work? So I'm also a little bit unsure about this one. Like in order to get the Wi-Fi module into the UART bootloader mode, I believe you might even need 1 extra pin. So yeah, I'm not really sure if we can do this. I'm just thinking that the Wi-Fi module, being able to make it unbreakable is very nice idea to me. So by having this connected, then you can connect the USB cable and sort of download a new firmware to the Wi-Fi module. If the Wi-Fi module dies for some reason, let's say we made a bug that is really stupid and it ends up in a bricked mode. If I recall correctly, SD in 1-pin SPI mode can get you a few megabytes per second. Okay, but megabytes per second, that is good enough. I mean, the largest ROM that we're gonna load is gonna be 32 or 64 megabytes, I guess. Something like, yeah, 64 megabytes. So even in 1 megabyte per second, yeah, sure, it will be a little bit slow, but yeah. So actually, I want to, just before we end this chapter, I sort of want to use this module, the C3, and I was looking a little bit at documentation for flashing it. So actually, let's go here to the issues. So I created a couple of issues on the GitHub to sort of structure up what we need to investigate. So this one is interesting to me because this sort of defines how many pins we need. There are some pretty nice over-the-air update libraries for ESP32, for what it's worth. That's cool. And that's really nice to have, but I'm still thinking, like, what if there's a bug in the bootloader or something that bricks it? Then having the UART boot, makes it possible for like a end user to just connect USB, hold down the boot button, flash like a special recovery firmware onto the Pico 2 with just dragging and dropping a file, because this is UF2 files. So anyone can do it from Windows and whatever. So I really like that. Full speed SD makes it possibility for streaming from the card directly. That's true. That's very true. And I really like that idea too. So how can we solve that? Can we share pins here? I'm thinking, as long as the Wi-Fi module and SD card are not active at the same time, we should be able to share these 3 pins with the SD card. And then chip enable, or I don't know. There is like no way to turn off the SD card completely, right? Like this doesn't have the chip select in the traditional sense. Again, I have I have way too little experience with SD cards. I've basically never coded to them directly. But from what I understand, you cannot really turn it off easily. So maybe we need like a switch to like really turn off. But then we need to boot it every time we need access to it. So if we download stuff from Wi-Fi to the SD card, we're gonna have to reboot the card many times. Maybe that's a bad idea. I don't know. It's a tough one. Or sure, we ditch this one and we get 3 more IOs and we are at 7. But I really don't like that. Rest of N64 handled by Pico 2. That's also a good point, but I believe, and this is something we also need to check and verify, that I believe that these signals are kind of slow, kind of I2C-ish speeds, but I'm not really sure. We need to figure that out. Turn off to share bus with Wi-Fi. Yeah, exactly. So from my understanding, which is limited of the SD card, is that you don't really have a chip enable pin which turns off the whole bus, like makes it floating, so that you're guaranteed that the SD card will not interfere with any pins. But by turning off the chip, well, maybe that's not either a guarantee. I don't know. Maybe that's also problematic. Like if you have 0 volt here, is there a guarantee that these pins are floating from the SD card? I don't know. There's so much I don't know about SD cards. So that is why I have them on 2 completely separate buses, so that they cannot interfere with each other. But again, we only have the 4. But yeah, I mean, if we kill this one, the UART, then we have 3 more extra here, which means that we suddenly have 7 free IOs. So now we have all of the pins. So, but that requires the Wi-Fi module to be perfect. Like if there is a single bug that can go into a bricked state, then we're fucked, and we cannot recover. Unless, okay, hear me out. Since we write our own code, we can pick pins for these. So what if we pick UART RX, UART TX, boot, and then we need 1 pin for the reset, I believe. I think that might actually work. So we have the set pin here. And then we just make sure to pick the right pins. So where can we? All right, we need to go to the actual module. We picked a nice module. Let me just find it real quick. We posted about it on the Discord. 1 second. Oh. There we go. Okay, so let's check the pins, because I believe we can. I'm thinking here, like if it makes sense to, yeah, exactly. So we would have to sort of bit bang SPI in that case from Wi-Fi, which I don't know. It could be fast enough. So this is the UART, and then we need the sort of boot and reset pin. I believe I believe it's this one, and then maybe this one or something. It's defined somewhere in the boot stuff here. There is good documentation for this. I have just not found it. But yeah, looking at the source code instead, you can see that. So we are doing this one. Yeah. Oh, maybe it's even supports SPI download. In that case, it's even better, because then those are probably actual SPI pins. So I really want to find the correct documentation. So if you could help me out and search for it as well, that would be really helpful. Because otherwise I'm gonna be really slow, I guess. Programming guide. Here we go. Okay. Control chip boot mode. Enable or disable ROM code printing to UART. Oh. Check it out. It has SPI boot. So if we use SPI boot, we don't need any UART. In that case, yeah, I believe maybe we want to have a reset, but make sure that these pins are the same pins that the bootloader is using as well. And then we sort of probably need to handle these strapping pins as well. Okay, ends by boot mode. It says normal flash boot. Yeah, we don't care about secure boot, so I guess this is fine. And I don't really understand what this means. It does not support security boot, and programs run directly in Flash. So it doesn't support this, and it doesn't support this. So what does it support? Only RAM, I guess? Will there be Raspberry Pi Pico-like board, just bigger and more pins? You mean by Raspberry Pi official, like from their own? I don't know. The main issue with the chip itself, the RP2040, is that there is only 30 GPIOs, and the Raspberry Pi Pico, I don't have it here, but it only exposes a few of these. Like it doesn't have, yeah, some of the higher numbers, which is why I'm using the RP2040 stamp for prototyping. So the chip RP2040 is being used in the Pico, and in the stamp. And here we have all of the pins pulled out or fanned out. But I don't know about the future of the Raspberry Pi Pico. I hope that they make a bigger chip. That would be really cool, but I don't know. Yeah, so going back to the bootloader stuff, let's see exactly how it works. What is a stamp? Okay, one second. Let's go here. Let's go here. So this is a RP2040 stamp. It is the same chip as on the Pico, exactly the same chip. It has a 8 megabyte flash. It has a reset button. It has power handling, so you give it 5 volt and it will just work, or you give it 3 volt or 3.3 volt and it will also just work. And it exposes all of the GPIOs that the chip has. In contrast, the Raspberry Pico pinout it has GPIO 0, 1, 2, 3, and so on, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 are not here. Also 29 is not here. It's yeah, it's a carrier. But are there downsides to exposing every GPIO? No? No, it's only upsides. In this case, I believe it's about the form factor, that they didn't want to make the board bigger. And also they used the GPIO 25 for the LED. So I believe it's a form factor thing. I can't come up with any other reason. So that is why I'm using this stamp in the prototype board that is currently in production. So this will help us to evaluate how to go forward. So this is all ideas and theory. We don't really know if anything of this will actually work and so on, but yeah, we still need to plan and experiment theoretically first, I guess. Yeah, correct. We really need all of the GPIOs for this project. Like if you just look at what we're connecting here, we're using every single GPIO on Pico 1 here, every single one of them. Not even one pin is free. And then for Pico 2, which is here, we are going to use all of the pins as well. So yeah, it's really, yeah, this project is really complex, but also fun. We're using all of the pins. We have this kind of funky bus with lots of chips on it and SD card, Wi-Fi module. Yeah, it's cool. So I just want to confirm, like that is like a big important task, to confirm exactly which pins needed for the ESP32C3 in SPI mode to start the bootloader in that mode. Like I believe maybe we can, what is it called again? Hardwire the strapping pins so that it always boots into SPI mode. But then you probably need one GPIO to sort of go into application mode and not bootloader mode. And then the reset pin is also important in order to be able to reboot the module. And if there is no reset pin, then we could have like a voltage, what's it called again? A power switch, where you control the, yeah, I don't have it here, but where you control the power supply for the Wi-Fi module if there is no reset. So looking at the module, yeah, this is the module. Let's see here one more time. The pinout was here in the beginning somewhere. Yeah. So here we have the 3.3 volt, the power supply, and we have ground. Then we have the enable. And I don't know if enable is the same thing as reset, maybe. And in that case, cool. do you want to store the program for the ESP32 on its flash or power it down in download mode, where you sideload the binary over UART? So I believe I want to. It's a really good question, to be honest. I don't know, because not having it stored on its internal flash makes it sort of more flexible, I guess. Then every time when it boots, depending on the size of the firmware, I don't know, maybe the firmware can be small, because I believe the ESP32C3 has like a quite big chunk of ROM with like library functions, like all the Wi-Fi stuff and so on. So maybe the application binary will only be like a few kilobytes, or maybe 100 kilobytes or something. And in that case, it could be stored either on the SD card or on the Pico 2's flash. But yeah. So the idea that JTH came up with was that the SD card should be like the central source of firmware delivery. So if we just look at the different flashes, the Pico 1 has no flash. Pico 2 has a small flash where we have a bootloader. And then the Wi-Fi module, yeah, sure, it does have flash, but we don't have to use it. And then the SD card is sort of very user-friendly to update. So the user puts like a binary, which I guess can be pre-built from a GitHub action, for example. And you just put it on the SD card. And then the Pico 2's bootloader will first just download its own application. So the Pico 2 firmware will be downloaded from the SD card. And now the Pico 2 is like online with the latest firmware update. And then it can toggle the reset pin so that the Pico 1 boots and deliver Pico 1 firmware from this blob. And now this is booted. And then it could deliver firmware, like you're saying, over the SPI in download mode to the Wi-Fi module as well. And now everything has the latest firmware, and you only need to change a file on the SD card, and you're done. So I really like that idea. It makes for a very smooth update process. No janky, weird stuff going on here. So I think that's a really good idea. So more research is needed, exactly how many pins we need here, how we hook this up. Yeah, so maybe just write the text here. Just so we don't forget about it. All right, so that is like the latest revision of the future. This is future v2, but we still need to think about it because yeah, when this all works, it will be a very like an actual nice flash card. And bomb wise, we have $1, $1, lots of dollars. Unfortunately, it is how it is. But no flash here and just a tiny flash here. So this is like less than $1. And then you have the SD card reader, or like the, yeah, what's it called? Socket connector. And the Wi-Fi module is like $3. So let me read the chat here. The more firmware flash stages make for points of possible fault, so we're trying to have as little as possible. Yeah, that's a really good point. So having this sort of delivery system where you put one binary or maybe multiple binaries on the SD card, and you have one bootloader that we basically never change. So we make this really simple, really bulletproof, and then it will download its application from the SD card, boot into it, and then you can do whatever you want to do. And delivering the firmware to the Pico 1 like so is also really cool. So yeah, I really like it. So I was actually researching a little bit about the Pico 1, the RP2040's boot modes. And unfortunately, it seems like it only has the USB bootloader. The USB bootloader is really good, don't get me wrong, but you don't like if you have USB, you could update the RAM contents and boot into it. But there is no UART mode for the bootloader, and not as far as I know. And the cool thing is that they even have the source. The source code of the boot ROM on GitHub. This is extremely cool. I don't know any other chip where they do this, but this is the source code of the boot ROM that is in every RP2040. It's extremely cool. So here you can see exactly how the USB handling stuff is done. This is so awesome. But I don't think it has UART. So yeah, let me continue reading chat here. Is the ESP32 planned to be used only as a Wi-Fi module? So yeah, initially we wanted to use it as an SD card proxy, like so that the Wi-Fi module is reading stuff from the SD card, and then the Pico 2 is sort of reading that through the Wi-Fi module. But that is a complex design, which is error-prone and requires software which is error-prone and takes time. So this makes for a simpler design. We need fast QSPI. Yep. By the way, this very boot ROM has some Easter eggs. Yeah, I know. That is really cool. I forgot what the Easter egg was, but you're totally right. I think it's 42. I'm not gonna spoil more. I'm just, 42, if I remember correctly. Yep. So, yeah, there we have it. So let's just do a control count of the number of IOs, because I've changed this so much. So we have. That is 31. Okay. So I guess we need to ditch maybe the detect pin. So we skip the detect pin from the SD card. So this one. And then we can just try to do stuff with the SD card and see if it works. And yeah, because we're sort of assuming that people will have the SD card connected at all times, like when we boot. So yeah. Yeah. So did I get that right now? Yes. So now we have, if this is enough, which I believe it might not be, I believe we might need one extra pin to sort of toggle the SPI boot mode, or we hardwire it into SPI boot mode, and we do what Jay Chillerup suggested, I believe, that we always boot into SPI mode, and then from SPI mode we sort of write firmware and boot into the firmware. That might actually work. So we don't really need to toggle the boot mode with pins. We just need to reset it. And actually, it's not called reset; it's called enable. So yeah. So at this point, I'm happy with this. So let's save this and update the PDF and do like this. So now we can leave this and start working on the PSRAM controller. So yeah, the question is, should I make a branch? Let's do that. And right, so where do we want to start? So I've connected everything on my desk. It's not very interesting to look at, but it's basically yeah, the Raspberry Pi Pico is connected to this PSRAM, and the PSRAM is connected through an interposer or test pin board, which the SLI logic is connected to. So we can sniff all of the PSRAM's IOs while still accessing it from the Raspberry Pi Pico. If I recall correctly, all of those chips can do USB host and client, so they could program each other over USB or put into a USB hub. Oh my god, that's really cool. Having a USB hub for like multiple devices like that, cool. But yeah, being a USB host, that is a can of worms, which I really don't want to open, because that's usually complex, really complex. Sure, it might work with the libUSB and stuff, but it's complex, and I really prefer to not do complex stuff. Like the SPI download mode, it sounds perfect, so I'm really, yeah, let's go with that. Okay, so where do we want to start? We can start by looking up the data sheet of the PSRAM and just have a look at the commands that we want to do. So these kind of remind of normal SPI Flash commands. Think this one, this one, this one. They're all, yeah, this one and this one too, kind of standard SPI Flash commands. It behaves essentially exactly like a SPI Flash, except that you don't need to do erase. So you just write 0 or you write 1, and that is what's going to be written. Because on the SPI Flash you need to erase first, which will turn every bit into 1s, and then you can turn a 1 into 0, but you cannot turn a 0 into a 1. But with PSRAM, you can. So if we look at the at the commands, just so we get a feeling of what we're trying to do. So this is the read, and this is the fast read, which is kind of funny. The fast read requires a wait cycle, while the normal read doesn't, but in turn, this one is only at 33 megahertz, and this one is at 104 megahertz. So I'm kind of curious. I want to use the 144 megahertz mode because we want to run this at 133 megahertz. And looking at the features here, yeah, it says 84 megahertz here, but that is because we can cross page boundaries. But we actually don't need that feature. Whenever we want to cross a page boundary, like we will not read like 1 megabyte of continuous data when in N64 cart mode. Again, just to people get a feeling of what we're doing. We are handling bus requests that look like this. Yeah, let's have these visible. So essentially, whenever a bus request is initiated and this read signal goes low, we have a time window to prepare data. And when it goes high, the N64 will latch that data. So during this time, we need to fetch data and present data on the bus. But it's only 16 bits at a time, which means we only need to read 2 bytes. And these 2 bytes will actually never cross a page boundary because when your reading address is sort of masked with 00, like it's 32-bit aligned, because all of the reads, as far as I know at least, are always at least modulo 2. Like you always get LSB and MSB, like the lower 16 bits and the high 16 bits, and you put them together, or it's the other way around, high first and then low. So the point is that whenever a read request is initiated, we will read 2 bytes, and then we will read 2 more bytes. but we will never read like 1 byte on one page and the second byte on another page. Like this 80 will be aligned, and then 37 will be 1 byte after that. So I believe that we never have to care about that page boundary limitation. So I think we can safely run at 144 megahertz. But the question is now, which command supports this? So in this table, it actually says 144 on the fast read and fast quad read as well. And what does this mean? Linear burst is prohibited. What was linear burst again? Was that the page boundary crossing? Yeah, exactly. Or no, maybe. Linear burst is probably that you just keep going. Because it's continuous. But we're okay with just doing 32 bytes because we will only do 2 bytes at a time, so it's not really a problem. Yeah, so basically this table tells us don't use read, everything else is fine. And don't do more than 32 bytes at a time, and don't cross page boundaries. So yeah, let's follow the rules. Okay, so here we have the fast read. This is really standard SPI flash stuff. First, you linear burst prohibited for write. Yeah, right. So I guess that means that we can only write 32 bytes per transfer or something like that. So here we have the write. But it doesn't really tell me anything more. All right. And then you have the QPI quad mode, which is actually what we want to do. So something that is a little bit confusing about SPI and QSPI and QPI, which is a journey we went through on the Game & Watch project, where we interfaced with various flashes, is that QPI mode, as far as I understand it, is that everything is in quad mode. So the command and address and data is all in quad. Whereas in normal SPI mode, you can perform a SPI quad write, which means the command takes up 8 clock cycles because this is still in SPI mode. But then the chip will realize, oh, this is the quad write. I will listen on all of the IOs. And then you come here with the address, and then boom, your data comes immediately. So that's really cool. So this is sort of a flexible command to use. The good thing with this is that you sort of don't have to change modes. So what we could do is to sort of have a two-stage thing where we send like a SPI command that goes into the quad mode, and then we can do everything in quad. But yeah, maybe we should start with just the easy stuff. So I guess, yeah, I don't know really. For sort of a bitbang solution, I don't know. Should I just take the code that I've already written for the Game & Watch stuff? Or should we start from scratch? So QPI write operations. Yeah, so this is really nice. So here you're always using the 4 IOs for both the command, address, and data. So this is, you see here, it's super fast. It's only 8 clock cycles from start to data. And then there should be a QPI read, I hope. QPI reset, input timing. Yeah, there we go, QPI read. Okay. So first we enter quad mode, and then was it chapter 14? Oh. Okay, it's on this page. So QPI read. So this is the one that we were gonna focus on. And here we still need a couple of wait cycles. But that is just how it is. So we have 14 clock cycles. So if you just make some quick math, we have 7.5 nanoseconds per clock cycle. So we take this times 14, I guess. And I probably messed up like this, yes. And then we want to make this into, I guess, nanoseconds. Right, so if I'm thinking correctly, this means that it's 105 nanoseconds from this time to this time. And then we also need 2 bytes. So we add 2 more clock cycles, bum bum, and we're at 120 nanoseconds. So ideally, in a perfect world, if we have a logic analyzer and we sort of raise a pin here, boom, and when we have the second byte here, we output the least significant bit on a pin, then it should be like 120 nanoseconds from this point to this point. And that is quite fast. So looking at this again, we have a budget of 310 nanoseconds. This is when the bus is in the 1240 mode. So this is the bus speed configuration. And looking at some profiling that I did a couple of days ago, I had constant data fetched from the C code. So yeah, just look at the main loop here. We have this is the main loop. We are getting an address from the PIO. So this will block until we get an address. So bam, we got an address. And later on, we're waiting for a write command. So the address will be 0 when that happens. So bam, we end up here. And then this is fetching the data. So essentially, this part will be at the very least 120 nanoseconds. At the very, very least. That is like a fact we cannot divert from. This is just the truth. And then later on in this other design, did I already close it? Yeah, I guess so. But anyway, we had this demux demultiplexer where we convert a binary number to 8 different chip select pins. And there we also need to sort of wait at least 1 or 2 clock cycles. So again, if we add that to the budget, 135 nanoseconds. But again, who knows? Maybe we can find a way to sort of, and that will be really, really, really hard, but maybe we can find a way to sort of make this cycle faster. So right now the cycle is 240 nanoseconds. And this is using just C code and a naive push-pull. So we're essentially just doing this, we could measure it, but just doing this is probably taking some significant amount of time, at least like tens of nanoseconds. I'm just guessing here, but I would assume so. Because I mean, there has to be some cost of doing this, like bouncing. So we're basically sending a 0 to the C code, and then the C code reads the 0 and does something and pushes something back. And that, yeah. So, but yeah, this profiling is basically from essentially from this spot down to this spot. So yeah, it is essentially as tight as we can do. Like, I mean, this is multiple instructions, but there's no real way around it. At least not that we could figure out. Yeah. Right. This again requires actual data from real games. How fast the bus may get configured. That is a good point, but I would really love to be able to meet this timing. That would be so cool, because then there's like no, like, then we're as good as the original games, which is a good goal, I think, to have. All right. So, GitHub issue for actual ROM research. Yeah, sure. We can create one. We can create one. 1 second. Let me just. Let me just open it up. Okay. Here we go. So, okay, research which PI timing are yeah, I guess something like this. There we go. By the way, N64 card slot breakout is for your own, is of your own design. Is it shared somewhere? So I was using the let's see here. So yeah, a year ago, so I made this ECP-Card64 hardware, and this design, I'm trying to remember exactly, but okay, 1 second. I'm just gonna open this KiCad project. Where's KiCad? Okay, 1 second. So this is the FPGA based flash card that I haven't finished. So this is using the ECP5. Thanks for the follow. This is using the ECP5 FPGA, and here's some SDRAM, and it's tightly connected here, and it has some flash and SD card, USB, power stuff, and I actually did this PCB design on stream, if I'm not mistaken. Yeah, I think so, but it was really kind of tedious, and it is what it is. Anyway, it's like 80% done. And this was meant to be like a proper, fully featured, really nice one. But I kind of lost interest along the way and sort of put it aside. And then, yeah, a couple of weeks ago, I had a look at this design again, and I was like, damn it, it's so hard to buy PCBs. So that's why I did the whole Pico stuff. But yeah, so this PCB shape is sort of borrowed from the Bootloader, if I'm not mistaken. But I did, yeah, let's see here. So, yeah, I think I basically based it on top of that. Because what we're looking at here is the breakout board that I made based on that other card. So this is like a stripped down version of that other card. Right. Okay. So you were actually asking about the breakout. So yeah, in order to find this, the Gerber files for this, you can actually find that on. Let's see here. Let me just dig a little bit. 1 second. There. And then breakout. I'm just gonna paste that here. So yeah, there you have the Gerber files, and I believe everything is included here. Yeah, the updated stuff, and also a zip file with the Gerber file. So you can just download this zip file and go to JLC and upload it there if you want to. Yeah, this project is, yeah, someday I will probably never finish this, to be honest. But it's yeah, the code, I've been using the code for researching and doing fun stuff with FPGA. So here in the gateway, everything here is sort of yeah, you have the software that is running on the soft core, and then you have right, I have a bunch of extra stuff here. Yeah, I mean it's a fun project, but I don't know, I will probably never finish it. Where do I have? Ah, there we go. Yeah, right. So here is the state machine for the cart, where it accesses the SDRAM and stuff like that. So all of that is open source. Nice. I was thinking that once people already go that far to order PCBs, Breakout may be useful for someone. Yeah, that is a really good point. And let's just confirm one thing. I want to see if pin 44 is broken out. It is not. Damn it. I hate myself. Why did I do this? So in the last stream, we sort of got the information from Corgo that pin 44 is the interrupt pin that you can use from the cart to inform the N64 that something is happening. So you can cause an interrupt to happen by toggling this pin. And yeah, for some stupid reason, you know what? Let's fix that. Let's fix that. Let's call this N64 interrupt. Oh, let's change the font. Oh, damn it. And we do like this. And then this one goes, where should it go? I guess pin 44. Oh no, I have a different pin configuration here. Oh, okay, we can put it there. So I guess the numbering is messed up because of reasons. And this one doesn't exist. This is to match it to my my board. So my board has this connector with these pin numbers. So I just used this as sort of a guide for myself for how to jumper wire everything up. But in this case, it's this pin. There we go. There we go. And I guess the Pico stuff at this point, you know what? Goodbye. Should I keep it? Should I delete it? No, I can keep it. And then we go into PCB and we press F8 and sort of, yeah, I suppose. Then we should have one net which is unconnected. Yeah. So and there you go. Now we have the interrupt pin. So if anyone in Europe, actually, I don't think I will need this myself, because in the future I will have. So we have the same bug in the PCB that I just produced. So we can fix that as well because we're streaming. So let's just not have any technical debt. Let's just do everything now, because then we don't have a to-do list. Yeah, so now you see here pin 50, 45. So this is pin 44. This is the new pin, and yeah, it's connected. Everyone is happy. So let's save this and let's plot Breakout. So what I usually do when I update stuff like this, just 1 second. Yeah, there we go. I have a bunch of crap. So then we plot it, and then we generate the drill files. Then we create a zip called N64 Breakout with a breakout directory. Oh. And this is the new KiCad stuff. Not really sure what that is. Maybe. I was trying to do something smart here. Yeah, I don't know. Let's just do and let's add this and this and this, I guess. I'm not sure about these. This is the new KiCad stuff, I guess. So yeah, this repo is gonna be kind of messy. It's a ugly fork, where I just forked the original, and then I just removed components and stuff and turned it into a breakout board. But then I believe this is everything. So add pin 44 and update the KiCad 6. Yeah, that should be fine. So there you go. Now you have a new breakout on, and it's on Git as well. So did I close that tab already? Yeah, it is the new stuff. So what you have to do to get a board, you just take this one, and you download it, you go to DLC PCB, and you just upload it here. Just press there, and off you go. One important thing, one really important thing. You have to choose 1 millimeter. This one. Otherwise it will not fit. Or you will use force and destroy your connector. Don't do that. So yeah, pin 46 is also connected to the video DAC, but I don't know what it is used for. Oh, for the video DAC. That one I've played around with a lot. Where did I find the schematic of that? 1 second, I'm just digging a little bit. Is it here? Yeah. So maybe you don't know Corgo, but I was I wrote some FPGA stuff to turn this into RGB data, and I used the Glasgow to sample this in real time, and I had it on OBS as well, so I could OBS stream live from the N64. So the raw RGB data went into Glasgow, and from the Glasgow through USB to my PC, and then inside the PC I turned it into a Video for Linux, whatever it's called, fake webcam, and then I used it in OBS, and that was kind of fun. So I implemented this whole logic. So my goal was to make a HDMI converter, but I know there's already solutions for that. The Pixel something. There are 2 different boards, so I don't really want to compete and whatever. But I just wanted to play around with it. So the code for that is actually on GitHub as well. It's a little bit hard to find because it's in a fork of Glasgow, I believe, and in a branch called N64. And here's all the software for setting up everything. So I wrote applets for both the audio and video. And I had this combined sniffer thing, which dumped both audio and video at the same time. But yeah, that was really fun. So yeah, in any case, okay, so one of these pins are connected to the pin 46. I wonder what that could be. Maybe the desync or something? I don't know. Wait, didn't we have a schematic? I didn't make a bookmark. think, yeah, it was this one, which was slightly wrong, but that's fine. We had a PDF here, if I'm not mistaken. Yes, there we go. Let's just add a bookmark. So what did we say? Pin 46. So that is this one. Okay, so it goes to this funky stuff. Yes. Okay. Oh, this is perhaps the American version, the NTSC version. Or maybe Japanese, but yeah, not the PAL version. I think this pin is used to synchronize video with capture cassette, essentially a composite video grabber. Oh, no, but that is a really good guess. That is a really good guess. But then that is on this side. So it's like the composite video out. Or it could be. So here we have the S-video. Well, doesn't matter. Doesn't matter. And we don't need that pin. But it could be fun for the breakout board, I guess. But at this time, I mean, we've already sidetracked quite a lot. What do I want to do? Should I fix? No, I want to get this. I want to get started with the PSRAM. So let's do that now. So okay. Where do we start? We want to start with creating a new folder called PSRAM. And let's just copy like the main file. There we go. Oh, not move. Let's call that PSRAM. I guess main.c, just to be extra boring. And nah, okay, let's call it PSRAM. So we don't want the multi-core stuff. We want to keep it simple, but we want this one, and we want this one. We don't want that. We want this. Yes. Okay. So this is like the bare minimum CMake file for our needs. Okay. Let's just clean up a little bit. Don't need that. We want this, we want that. Yes. I don't know. Don't need that right now. Yeah, we could overclock, but yeah, let's skip that right now. We do this, and yeah, sure. We don't need that. So this is important. The PIO stuff, let's just comment that out for now, and then skip that, skip that. I guess now we can just do something like so I don't know. Where do we want to start? We could I haven't really thought a lot about how I want to design this. You just know that this is work that has to be done. Looking at the Pico examples, there is actually a SPI core. Oh, this is using the normal SPI peripheral. We don't want that. We want the PIO SPI implementation. So I've just had a really quick look at this, but I believe that there is some documentation here. But looking at the PIO file here, it speaks about full duplex SPI. So I interpret this as that you're receiving data and clocking out data at the same time. And we don't need that because, again, looking at the protocol here, it is half duplex. Duplex meaning that both we and the other party can speak, but half duplex meaning only one can speak at one time. So first we send a command address, and then we wait, and then we continue to drive the clock, but now the chip is responding to us. So we only need half duplex. So looking at this, it's a little bit over complex. Because we don't want the full duplex stuff. And then reading a little bit here, it says auto push and auto push pull must be enabled. The serial frame size is set by configuring the threshold. Shift left right is fine, but you must justify the data yourself. This is done most conveniently for frame sizes of 8 or 16 bits by using the narrow store, replication, and narrow load byte picking behavior of RP2040's PIO fabric. Okay. And then you have those clock phase thingies, like when the clock is rising or it's falling, whenever you should sample the data. And that is sort of described here. Yeah, you see the rising edge, that is when the chip will sample the data. So first you change the state, and then you update the clock. But I'm wondering, will we actually run at 133 megahertz, or will we run at 133 divided by 2? Because essentially we will have to do like set clock low, change pin, set clock high. But I guess that is handled in some super tight loop here somewhere. So let's read this code and try to understand it slowly. I guess that's probably a good idea. So clock phase 0. Data is captured on the leading edge of each pulse. So the leading edge is the rising edge, I suppose. And transitions on the trailing edge. So when it falls, that is when you do the transition. Yeah. Okay. Oh, this side stuff. This is the really complex, or like the advanced PIO stuff. Let's worry about that later, I think. So what do we do here? 1 second. Yeah, just 1 second. I have to do something. All right. And clock phase 1 is the opposite. So, but in our case, we do this for sending data, and then for receiving, it's the other way around. Okay, so how does it work? We have some C code that does some stuff. What does it actually do? We have the PIO, the state machine, the offset. That is sort of the boilerplate stuff. Number of bits, clock division as a float. Wow. Okay. Polarity, and then pin. It sets up the out, in, and side set pins, right? Okay. Right. This is the right. We learned a little bit about how this works when we implemented the PIO stuff, but I've already forgotten what these different calls mean. But yeah, we can learn that again. And set pin tiers, right? That is the input output. Yeah, in order to use the pin tier stuff, you need to define what you can do, right? So just comparing with our own code, which I sort of understand a little bit more. We have this consecutive pin direction. Yeah, right, because we have a range of pin directions. So, right. It's a little bit different, but yeah. Okay. Pin maxes can be configured to invert the output. Oh, that is cool. This is a really cool feature. I didn't know that. So if I understand this correctly, you can sort of configure the GPIO to, when it gets a 1, it actually outputs a 0, and the other way around. That is cool. Didn't know that. Set out over. Okay. Just want to see the documentation for this function call. So I guess it's here. Right here? No. Here. Here we go. Output override. Okay. So here we can do the invert stuff. Okay. Cool. Yeah, this was interesting. But yeah, going back to the PIO code, and there, yeah, right. So if CPOL is 1, we do the invert. Otherwise, we don't. That's, yeah, nice. Okay, SPI synchronize, so bypass input synchronizer to reduce input delay. Oh, okay. So is this the 2 flip-flops, I suppose? Yeah. Yeah, exactly. The 2 flip-flop synchronizer on each GPIO, which protects PIO logic from metastability. Feels kind of scary to disable that. But okay. Okay, so what was this? This was just setting up the pins. Okay. SPI with chip select. For your amusement, here are some SPI programs with an automatic chip select. Asserted once data appears in TX50. Deasserts when FIFO bottoms out. Has a nice front-back port. Okay. Number of bits per FIFO entry is configured via the Y register and the auto push-pull threshold from 2 to 32 bits. Pin assignments. Clock. Chip select. Okay. This makes life easy, I guess. Yeah, so I guess what we should do for the quad stuff is to also have like the IO0 at bit 0, so that we can do like pull 4 and or in pins 4, stuff like that. Yeah, and this is the capture. And in our case, the data is captured on the leading edge. Okay, but in our case, it is actually the opposite. We should capture data on the falling edge. See here, on the falling edge, that is when the data is stable. So we want CPHA1, so this one. Okay. So what does this actually do? This is probably the big magic. Yeah, this is the actual implementation. So let's read this and try to understand exactly what it does. So wait a minute. Yeah, exactly. I was thinking like, wait a minute, we don't have anything in our output shift register, but this is actually the entry point, and then we loop in a funky way. So just some background on the PIO stuff. This is basically the start of the program, And this is the end of the program with a feature that makes it loop. And then this public entry point tells the program to actually start at this instruction. So, okay, so let's read the code as it happens. So the code is booted, we jump here. Full, if empty. Which means that if the output shift register is empty, only then we will block here. It just clocks on every micro op, basically. Right. Yeah, I just need to sort of read this code slowly and try to understand it. Okay, so we are here. We block here, but only if the output shift register is empty. So let's say that we read a bunch of bytes or bits, then we will not do anything here until it's empty. And then this side OX2 square bracket 1. Yeah, this is a little bit funky. So let's open up the Raspberry Pi Pico, no, RP2040 PDF. The datasheet, yes, and we go to the instructions, and we go to pull, and so the no block, it checks, yeah, if right, if empty. Oh, actually, so we don't have the block and no block stuff, so we're only using if empty. And what did if empty mean? It probably means if the output shift register is empty. Yeah. But how did the side stuff work? So here we do the side set 2. Remember the side step, that was the fancy stuff that made it possible to use this block many times, but for different IOs, if I'm not mistaken. But we don't have to care about that because we're sort of we can just hard code whatever we want to do. Right. Control flow, registers. Right, so we do the side set 2. So let's just read what it does here. If this directive is present, count, which is 2 in our case, indicates the number of side set bits to be used. And if you, yeah, I think we set up the side, yeah, here we set up side stuff here. So we set it to the clock. Okay, so this makes it possible to use. Yes, I'm still kind of iffy on how this works. Oh, okay, I'm looking at the wrong thing. So this configuration goes with this PIO, right? So how do we do the side stuff here? Okay, same thing. Yeah, it was the square brackets that was some delay, right? So still not really 100% about what that does. So what was the default here again? So we didn't specify blocking. So I guess blocking is 1 by default. Oh, welcome readers. So we're currently learning about the PIO, the Raspberry Pi Pico fancy I/O handlings, in order to implement a PSRAM QSPI controller on the Raspberry Pi Pico. Thanks for the follow. And yeah, maybe just gonna give a quick background here. We're currently designing a flash card for the Nintendo 64 using a Raspberry Pi Pico. And in this hardware architecture, we're sort of forced to do some creative stuff. And right now, yeah, that is implementing a PSRAM controller using QSPI. But since there is no QSPI peripheral on the Raspberry Pi Pico, we have to implement it ourselves. And looking at the examples, there is a SPI example, but it's only SPI, and we need QSPI. So that is what we're gonna try to implement here. So yeah, that's where we are. So currently I'm reading the example here and trying to understand exactly how it works. And I'm still kind of iffy about how the sidestep stuff works, so I'm not really sure how it works. But essentially, yeah, we're looking at the pull instruction and how that works right now. So, okay, so pull if empty. So definitely more impressive than what I had done. All I did was make a face cam behave like a DVD screensaver. That's fun. That sounds fun. Yeah. But anyway, welcome. And I'll try to explain everything that I do so that people can follow along and maybe learn something. This kind of stuff is always like magic to me. All right. Oh. Yeah, OBS can be a bit weird sometimes. Thanks for the follow. Right. So yeah, this code is also using a feature called auto push and auto pull, which I haven't really learned how to use. So I'm also a little bit unsure about how that works. Yeah. So anyway, so the entry point of the program is here. We're pulling data. Like the code that I had written before to perform the Nintendo 64 I/O handling, I simply do push and pull, which just to explain how the default behavior works is that we have a special register called output shift register and input shift register, which push and pull can yeah, interact with. So yeah, push means it takes the output shift register contents and sends it to the let me think here, to the C code, right? It's yeah. So push and pull is the interaction with the FIFO. In and out is the interaction with the pins, right? So I got a little bit confused about that last time. But yeah, so in this case, yeah, we're pushing a 0 to the C code, and then in the C code we are blocking here until we get a something. And if that something is 0 or not 0, we do different stuff. Oh, is that the stack smashing? Or which video is that? Let me just check it first. Yes, okay. Let's watch the video together. I'm gonna mute my music and okay. So maybe this will be loud. I'm enabling my desktop audio. Let's play.
With each instruction, we can toggle the IOs mapped as site set. For example, by adding site 0, we turn the site set IO off, and with site 1, we can turn example.
Okay, let's take
bits.
this whole
However,
section.
The amount of bits available as delay depends on another functionality called site set. Site set is the only GPIO group we haven't looked at yet, and it's used by a pretty cool feature. With each instruction, we can toggle the IOs mapped as site set. For example, by adding site 0, we turn the site set IO off, and with site 1, we can turn it on. We can set and clear 5 individual pins this way. Pretty sweet. This is super useful when implementing fast clocked signals such as SPI, as we can toggle the clock at the same time as we are shifting data out. To enable site set in the assembler, we need to specify the number of IOs we want to use as site set, using the .siteset directive. Note though that each siteset pin will reduce the bits available for delays by 1. Now by default, if we enable siteset, we have to specify the value of these siteset pins on every instruction. However, if we add opt to the siteset setting, this becomes optional and the siteset pins will just retain the last set value. This comes at a cost though, as it will reduce the number of bits available for delays by 1 more. Siteset can also be configured to set pin directions instead of setting IO values. This is enabled by appending.
Yeah, nice to have you here, and you're welcome to come next time. Thanks for coming by.
Pin years to the siteset directive. Finally, let's talk about program wrapping. A lot of PIO programs will consist of what's basically an endless loop, and normally when the last instruction...
Right, the program wrapping we've understood. But yeah, the sidestep, like even if I feel like a stupid student, I hear the words, but I don't get it. I have to watch it one more time.
We can toggle the IOs mapped as siteset. For example, by adding site 0, we turn the siteset IO off, and with site 1, we can turn it on. We can set and clear 5 individual...
Right, the delays, I only read about them. You know what? Maybe we should do like a test with just playing around with delay and sideset and look at the SLI logic and just learn by coding. But yeah, let's watch this section as well.
Now before we finish, let's have a look at 3 more features. The first one is the delay functionality. If you read PIO assembly, you will often see numbers in square brackets at the end of the line. These are used to increase the cycles an instruction takes. Normally, any non-blocking instruction takes exactly 1 cycle. Now often we want to perform cycle-precise I/O for timing.
Thanks for the follow.
Reasons. And let's say we want to create a square wave. This code has 3 instructions. The first one sets the I/O, the second one clears it, and then we jump back to the beginning. Now in this case, our square wave would look like this.
Right.
The 1 is half the length of the 0. Not great for a square wave. Now we could insert an additional no operation instruction that just wastes time. For example, move Y to Y, which does literally nothing. This gives us a perfect square wave, but it also wastes 1 instruction slot. Luckily, the PIO language has the delay feature. Instead of doing this, we can simply add a 1 in square brackets behind our first instruction, and now the instruction will execute and then wait for 1 more cycle. We still get the perfect square wave, and we've also regained 1 instruction slot. The delay can be between 0 and 31 cycles, aka 5 bits. However, the amount of bits available as delay depends on another functionality called siteset. Siteset is the only GPIO group we haven't looked at yet, and it's used by a pretty cool feature. With each instruction, we can toggle the IOs mapped as siteset. For example, by adding site 0, we turn the siteset IO off, and with site 1, we can turn it on. We can set and clear 5 individual pins this way. Pretty
now I get it.
This is super useful
now
for
I get
implementing fast clocked signals such as SPI, as we can toggle the clock at the same time as we are shifting data out.
Right, so in case anyone is struggling like me, side 0 sets the side set pin to 0 and side 1 sets it to 1. So this is like a free extra GPIO output per instruction. Now I get it. But it's limited to the side set pin, which in our case is the clock. So whenever we call pull, we do the pull, but we also set the clock to 0. And then we do the jump loop, and we also set the pin to 1. So it's a free GPIO output. Now I get it. Good video. just a slow student. Okay, but that was great. Let me mute. Yep. All right. Yeah, thanks for sending the link. Yeah, that was nice. So now we get it. But now I'm getting confused again. How can you do side OX2? I thought it was only one pin. Here you do sides OX0, OX1, but what the heck does OX2 mean? Does that mean, oh, that set pins actually sets the base pin. So 0 means, or like bit 0, because we're talking about bits here. All right. I think I get it. So so essentially, this is the 32 output bits, and the LSB is mapped to the clock pin. So 0 and 1 is this pin, and then 0 and 2 is this pin. So it's like clock, the pin after clock, which is probably the chip enable. So there's probably a requirement of the chip enable pin. Yeah. Here you see. Here it's actually documented. So yeah, this confirms my understanding. So you set the offset, the pin offset to whatever. Now I get it. Cool. So again, now we can read the code and actually understand it. So pull if empty means that we only do this if it's empty. We toggle the chip enable, or we actually set the chip enable pin. Yep. And then side OX0 means that we clear both the clock and the chip and yeah. Okay. So this actually sets, yeah, block with CSN high. Yeah, it actually says here. Yeah. Okay, now I fully understand what this line means. Okay, then we pull CS low, and the clock is low, and now we start looping. So we output pins 1. So that means that we take the 1 bit from the output shift register. We consume 1 output shift register bit. We write that to the pins pin, which means the meso pin, because we're only using 1 bit here. And then we do the sidestep thing where we set the clock high, and then we wait 1 cycle, and then we read 1 bit from the meso, I guess. Yeah, exactly. And then we do the sidestep thing. Yeah. And then we do the bit loop. And we do this until x becomes 0. But what is x? In this case, we set x to y. And what is y? It is not even set here. This is confusing. Because move is x equals right hand, like it's this, right? Or in FPGA style, like this. We can double check, but no, we can actually look at our own code, because that I know how it works. Read all pins into O, sorry, yeah, exactly. So you take this and put it there. But this I do not get at all. Where does y come from? Must set xy to n-1 before starting. It actually says there. Right, so they're using the fancy stuff where you can actually yeah, you do this. So actually, let's talk a little bit about what this does, because that is actually really cool. This lets you execute one instruction in the PIO from C code, and then you encode an instruction. And in this case, you encode the set instruction, where you set x to the value of n bits minus 2. So this initializes the x and y variables. But I'm also kind of... Right, we never change y. And then here we initialize x2. So we're basically performing this step already here. Okay, now I get it. So let's go back here again. So yeah, we do this thing. We loop until x is 0, right? And then what is this? We output pins one last time. We move y to x, so we reset the counter. And then we input pins, and then we jump, if not OSRE. What is that? Let's read about that. Output shift register not empty. Which means that we have this tight loop until output shift register is empty. And that we consume 1 bit every time this happens, and we consume 1 bit every time this happens. So this code only works for an even number of bits. Like if you have 7 bits, it will not work properly, I suppose. But yeah, that's interesting. Okay. You know, I can now confidently say that I fully understand this code. But that took a while. And I hope maybe if you're watching, you also feel that you understand it. But yeah, this is all new to me, and probably new to most people. So let's just learn together and try to understand it. So the auto push and auto pull stuff, then what is that all about? Here we don't really use auto push and auto pull. We do pull. Okay, the auto push comes from in. Right. So is that called auto push? Because this is an implicit push. Whenever the output shift register is full, it will do a push. Yeah. So where is that configured? Okay, not there. Maybe in the other code. No. You configure. Okay. Auto push. How do you do that? Okay. So let's read one more time. Auto push and auto pull must be enabled, and the serial frame size must be set, or is set by configuring the push and pull threshold. Okay, so maybe let's search for the threshold, and maybe it's called somewhere in the SPI stuff. Just gonna search in every file here instead. I'm really confused. Where is it being set up? Because it's this. Okay, let's read about this. Okay. Okay. with each out instruction. The output shift register gradually empties as data is shifted out. Right. Once empty, it must be refilled. For example, a pull transfers 1 word of data from the TX50 to the OSR. Yeah. Similarly, the ISR must be emptied once it's full. One approach to this is a loop which performs a pull after an appropriate amount of data has been shifted. And I think this is the approach that we're using in the N64 cart stuff, where we do explicit push and pull. So, yeah. Yeah, it wastes some instructions and the throughput is not good and so on, blah, blah. So okay, so this is where it gets interesting. So on an out instruction, which reaches or exceeds the pull threshold. So let's say you start with filling, you have 32 bits and you are consuming bits of the bits and suddenly there are 0 bits left, okay? The state machine can simultaneously refill the output shift register from the FIFO if data is available. So that is really cool. And on an in instruction, so that means that out, it doesn't block, or does it? Because if it's not available, what happens then? I don't know. On an in instruction, which reaches or exceeds the push threshold, the state machine can write the shift result directly to the RX50 and clear the ISR. Right. This. Oh, right. You do this .program auto pull. So, but do they do that here? No. They don't. So I don't understand this. Okay, this is just the name of the program. But what do they do here? They do out pins 1, side 0, wait 1. Okay. So does that mean that auto push and auto pull is like always enabled by default? Because that seems confusing. Yeah. I mean, this looks really nice. We're just, yeah, we're toggling the side pin and we're just looping here super fast. Yeah. So shift, control, pull threshold is reached. So the same program could also shift out 16 or 32 bits from each FIFO wall. Yeah, so where's that configured? Right, pull if. So, okay, okay. So here they actually control this stuff. There we go. Okay, so maybe I should search for this. So do we mess with that here? Nope. 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 It's only the I2C example that actually does it. So this is an example which actually configures the auto push properly, I suppose. So maybe I'm still confused because the code clearly says here that if it's supposed to work, it has to be enabled. But they don't enable it. Let's just read all of the code and all of the comments and try to figure out what the heck is going on. So this is write 8 bits. Yeah. Read, write. This does the full duplex stuff. So it reads and writes at the same time. Right? Okay. So okay, this already looks a little bit funky. Okay, so it writes to the TX FIFO with the dereferenced source pointer, which is increased. Okay. And we have the counter that goes down. And here we read, but we don't care about the data. But we make sure to empty the FIFO, which is good, so it doesn't get stuck with the stale data. Okay, so I guess it just pulls data, and I mean, it just pushes and pulls data. Nothing strange. Okay, now that I read the code properly, I think I understand this. Seems pretty straightforward. Okay. And here's actually an example that interacts with Flash, which is perfect for our use case, because we also have Flash-ish. And it does exactly what we want to do, more or less. It does read, it does write enable, I guess. Okay, so you create the command address, and you manually toggle the chip select pin, which is funky. Why do you do that? Didn't they do it in this sidestep thing? Yeah, that seems kind of unnecessary. Anyway. Yeah. This seems pretty straightforward. Flash write enable. Okay. Sector erase. Page program. Right. The page program, what was that again? OX2. That should basically match the write, yeah, SPI write. Yeah, so this is page program, but it's also SPI write in our PSRAM. We should actually be able to run this example on the PSRAM, and yeah, let's just do that. So I'm gonna adjust this example. So our pins matches. Like, I don't want to use these pins, but it's kind of hard-ish coded for those. So I guess let's just hack this a little bit. So let's do undefine this one. Right. So 1 second, I'm just gonna get one extra chip. Oh, I actually have one here at my desk. So let's read the pins here. We have we start at 16. 16 is pin 1. Oh, that is the clock. So that is 16. Yeah. And then we have MISO, which is this one. Oh, these are actually in order. Thanks for that. that is actually 17. And the chip select pin. Oh, that is. And then we have the chip select pin, which is on pin 19. Right, so one issue that we have here is that we have the chip select pin not adjacent to the clock pin. So this is gonna not work. Damn it. I don't want to rewire everything. But maybe I have to. Or we could actually change this. Let's just comment this out. We don't want the chip select stuff, because that's gonna mess up everything. Okay, then we have the configuration. Yeah. Okay, and they use like a huge, really slow clock, which is fine. Okay. I'm looking for something. What was it again? Right, we also need to change the UART. 1 second. We should change that to whatever we have here. There we go. So, and then we just copy this, put it here. Yeah. So, oh, some builder. Okay, so now we have built this, and now it's time to flash it. So here's our serial port, and now it's time to do the open OCD stuff. But first, there we go. And we don't need to mess with the flash size. Yeah, let's take this one. Okay, so now we're actually flashing the SPI example, but there's nothing on the UART. It could be that I messed up the wiring. Let me just flash this one. Yeah, this one. I'm just gonna comment out the ROM so that we don't waste time on that. Right, there's a huge H file containing lots of stuff. Maybe I should comment that out as well. Yeah, there we go. Much faster. So the goal of this is we want to see the okay, I must have messed up the wiring. So 1 second. Okay, there we go. I had connected it incorrectly, which means that we can now use the SPI stuff. Oh, check it out. It did stuff. Most of it is 0, and it's still 0. Okay, doesn't look very good. I guess that's, yeah, something is wrong here, which means that we can open up SLA logic stuff, which for some reason, there we go. So yeah, can you save this view? I guess not. So we're gonna have to relabel this. Yeah, 1 second, I'm just looking here. Oh, I'm thinking upside down. That is why. So these are mixed up. It's 19, 18, 17, 15. Let's try one more time. Okay, still no good. So yeah, good thing is I have the logic analyzer hooked up, so I'm just gonna make sure the pins are in the right order. So first one is chip enable bar. Second one is MOSI. And we have MISO. Then we have the clock. And then here we have PIO2 and PIO3. And we actually don't need those last signals. We can sample a little bit slower. There we go. Okay. Okay, stuff actually happened on the bus. That's good. All right, we can actually add a decoder. So we'll see MISO clock chip enable. And we have this one and this one. Okay, by the way, have you tried Sigrok Tools View? Yes, and I like it, but for the SLA logic, I have the 8 SLA Logic Pro 8, and it's not compatible with the Pulse View last time I tried. It might be compatible now. But yeah, okay, here you can clearly see that we messed up the pin numbering, that this is obviously the clock. So I think maybe I should go back to this. But no, I have to, let me just, yeah, give me a second. I have to read. Okay. So the wiring looks good. Yeah, so the wiring on the sniffer or like on the SATA logic, they definitely go in the correct direction. So this is correct. Chip enable MOSI MISO clock, and then we have the IO2. Oh, wait a minute. Oh, wait a minute. Did I mess up? No. This is really strange. I don't get it. Like, sure, I can run it like this, but it doesn't feel right. Something is odd. Like, maybe it looks correct now? No, okay. It doesn't seem to bite. These... Something is odd. Maybe this is reused somewhere else in the file? Oh. Oh, hey. Welcome, Bitsint. So just to give some if you just joined, we're currently implementing, or we're currently trying to run an example about interacting with SPI Flash using the Raspberry Pi Pico's PIO, the programmable IOs. So just before we had a deep dive into the PIO code, and we think that we understand it. And now we are trying to run the example using some SPI PSRAM that I have hooked up to the Raspberry Pi Pico. And yeah, I want to change the IO numbers here without sort of hard coding stuff, but it feels like it's not really enough, because even if I change the IOs here on the logic analyzer, we still seem to be using this pin as a clock, which is this not supposed to be. So yeah. Tjena tjena. All right. Yeah, so let's try to figure out how this works. Thanks for the follow. Yeah, so here we are initializing the PIO with these pin numbers. And looking here, we're using them here. So I mean, it should really work. I don't get it. I mean, we could also just hard code it in case this define stuff doesn't really bite. So in that case, let's just do that. So for the clock, we had pin. TX is the MOSI pin, 17. and then 18 for this one. I guess the one of the issue is that the chip select pin is supposed to be the one next to. Let's see here. All right, maybe we're not using the correct program. We're supposed to use this one. So we have to set this flag to true, CPHA to true. Right, and we're not. So let's fix that. So let's try again. Okay, still only zeros, but are we toggling the right pins? That's the question. Boom. No, this is getting really annoying. So, okay, I'm gonna rewire it then to use the default pins just so we get a good start. So let's do like this. But I still want this one to be true. Right. So now we need to look up what these pins are. There we go. So, okay. So it's actually really close. That's why. Okay. So I'm just gonna connect some wires. It's gonna be a little bit quiet for a while, I suppose. Okay. So RX, that is the meso pin. Should go to pin 16. Okay. Okay, and then 17 is the chip select pin. Oh, this is also a little bit odd. I thought the... yeah, never mind. Okay, then pin 18 is the clock pin. Yeah, sorry for this. I wired it before, but yeah, didn't really work out. So okay, there we go. So finally it's wired up correctly. And we can run the example. It's still getting zeros. That's weird. But do we get the right signals? It still looks kind of... Okay, I should revert my changes because I did some changes Yeah, there we go. Let's try it one more time. I was too slow. Okay. So it seems the chip enable is always slow, which is strange. But you can see that there's, and also the pins are all, yeah, okay, because they are rewired here. Okay, so maybe this is the chip enable actually. Yeah. Because now we're using a different pin mapping. We're using this one exactly. So we have RX. Okay, one more time. So this is actually RX, so that means meso, and then we have chip select, and then we have the clock, and then we have muso. So this is the command going out. So now the SPI analyzer, let's just remove it and add it again. So musi, miso, clock, chip select. Now it works. So now the analyzer understands the commands. This might be a little bit small to read on the stream, but I'm not sure if I can make it bigger. If anyone knows, let me know. Oh God. Okay. I don't know how to make the interface, how to zoom it in the sort of, yeah. So never mind. But we can look here at what's going on. So we do the chip enable, and then we clock some data, 6, and then we clock out some data. So is 6, is that supposed to be correct? Let's go here and here. Yeah, it's supposed to be the right enable, but I don't believe we need to do that, to be honest. So let's just skip that. So we skip that. And because if we look at the data sheet, we should be able to just use the SPI write, which is command 2, and just immediately we just write the, where is it? Here. We write the 2, we write the address, and then we clock in the data, and that's all there is to it. So yes, let's just comment this out. Yeah. Sector erase, we don't need to do that. Yeah. All right, we need to build this up. Oh, shit, I forgot to build. That was really stupid of me. Okay. Something seems fishy. Okay, it's gets stuck here. This looks really okay. Let's just revert more than. I mean, I really shouldn't need to do the write enable stuff. That should be fine. But the CPHA we should definitely have to true. We should set that to true. Okay. Now then. Okay, so it gets stuck. Probably because something is wrong with the pen modes, but now I actually wire it up as it's supposed to be. So oh, okay, here we go. Check it out. Okay, so this actually looks good. So this is actually random stuff like SRAM or SDRAM. Anyway, the RAM cells contain entropy from being in a state of flux when powered on. So this is random-ish data. As you can see, there's a pattern to it, but it's not initialized. Then after program, it looks like we have a counter 1, 2, 3, 4, 5, and so on up to F. And this actually looks really good. And this kind of proves that the erase command has no use. It doesn't do anything. Okay, now we're back at like square one. We have the example running. We have wired up the flash, and it's connected in the way that the default pin mapping is. So it's connected in this way. And now just to have the SATA logic sort of confirm what we see, let's just have a look at that too. So let's just run it again and stop it. And now it all looks much better. So here you can see the chip select goes down. Okay, let's remove that. SPI. And then keep those at 0, 0. But for some reason, it doesn't really trigger on this one. Oh. I'm incredibly confused now, because this definitely looks like the chip select. So have I actually wired up the logic analyzer incorrectly as well? No. This is... It doesn't make any sense. These numbers are correct. 0, 1, 2, 3, 4, 5. But I mean, this, as you can see, this is clearly chip enable. This is the MUSI, and this is MISO, and this is clock. Because here we are sending data, and we are receiving data here. Does not make any sense. So getting confused by these names because I'm kind of remapping it to reality. So let's go from the top. We have the chip enable. It is this one. Then we have the MUSI. It is this one. Then we have the MISO, which is clock. Yeah. And then we have the actual clock, which is on the MUSI. Right. Yeah, now it makes sense. So now we have the 6. We have some stuff here. So read is supposed to be, is it 3? Yeah, exactly. So here's the command read at address 000. And then here we get the data until the chip select goes high again. Yeah, so this is like the read burst. And then here we have the write, and then we read it again. Yeah, so that all makes sense. But yeah, I don't understand what's wrong with my wiring because it's really doesn't make any sense. So I double checked, and even so, it's messed up. Oh, right. I get it. Oh. So these labels are whatever is on, yeah, what it's supposed to be. Yeah. I'm just a little bit confused because rewiring stuff, when you have labels, it's extremely confusing. Yeah, because I want to have these mappings. But anyway, now we have something that works and we have a baseline. I just kind of want to double check, like if you go here, does it make sense here? So does this actually, yeah, it doesn't really. Because this is the clock, clearly. I don't know, I give up. Yeah, so if I look at my logic analyzer, the pin 1, like the pin or GPIO 0 or whatever you want to call it, that is hooked up. Yeah, to the pin 1 on my PMOD. Oh, sorry, pin 1 on my PMOD, and looking there, that should be chip enable. Oh, and it is. Yeah. Oh, now crap. Because I rewired it, I confused myself like 3 times. So the logic analyzer is connected the way that it's supposed to be. So here it should be chip enable, here it's supposed to be MUSI, here it's supposed to be MISO, and here it's supposed to be clock. And then on the other side, on the Pico side, this is not 16, 17, 18, 19, but it's all jumbled up in this mess. So that, okay, that explains everything, and that also explains why it works. So, okay. Yeah, stupid tangent. Sorry for being confused, but okay. Now we have a baseline. So what do we want to do with this? Do we want to make this into a quad SPI instead? So in order to get quad SPI to work, we would need to reshuffle the pins because it doesn't make sense. We need the pins to be in series. So we need to have IO0, IO1, IO2, IO3 after each other in the GPIO mapping. Otherwise it will not work. And with GPIO mapping, yeah, I simply mean that if you just look at the PicoCart, yeah, sure. It needs to be in sequence. So essentially, this wiring will not work. Actually, this is, god damn it. Yeah, this will not work. So the PMOD mapping is bad. This is bad. Yeah, this is really bad. Because we need these to be in series. So that's really confusing. I'm writing some extra information for the README about doing your own boards. Oh, that's really nice of you. Thank you. Quick question. Are you going to solder the few components on the board yourself, or do the LCC assembly service? Seems the BSS84 is mostly out of stock on Mouser. Okay, so a few things. I've only ordered the boards as PCBs. So I will get these PCBs and then I will solder this by myself, and I will solder these components by myself too. So the passives here are really not much. So the ferrite bed, you can, if you don't have a ferrite bed, you could just put a solder blob like a 0 ohm resistor here, bulb. These guys are 0603 5.1 kilo ohm resistors. They are needed for the USB-C stuff. But if you have a USB-C to USB-A cable, you don't even need to connect those. That's only needed if you have USB-C to USB-C. And then this resistor, you could also replace that with a solder blob or so. It's connecting the shield to the ground, and usually it's a 1 mega ohm resistor. You can also put 100 kilo ohm, but yeah, it's nothing critical. This switch is just a button. It's needed in order to get the RP2040 into bootloader mode. So if you don't have a button, you could use a pair of tweezers and hold them here while plugging in USB. That is totally a valid way to do it. Or you connect to these pins, which are the SWD debug pins, to a debugger. For example, a Raspberry Pi Pico, which is kind of funny, but yeah, you can use a Pico to debug a Pico. And then here we have the SD card holder or connector, which is not strictly needed. And this is a PMOD connector, which I was planning on using as a sort of IO expander to experiment. But as we just learned, having, a PMOD compatible SPI or quad SPI flash is less than ideal because these pins are not in sequence. So the sequence is basically 1, 2, 3, 4, 5, 6, 7, 8. So yes, you can see this one, or this one actually. Did I wire this incorrectly? Right, because I wired this up to match the SPI peripheral. So these are actually connected like the SPI peripheral is mapped out on the GPIOs. So we have the safe select, the clock, IO, and chip select. Yeah. So these pins are connected in a way that the hard SPI block is configured in. This really, but it's not the end of the world. You can still rewire it. So I guess later on when we have the QSPI controller ready, we can hook up the RAM in a different way, so that we essentially get the IO 0, 1, 2, 3, 4 or 0, 1, 2, 3 in sequence. So yeah, that's kind of annoying. So I guess what I should do now is to break out the example, because I guess it's a really good starting point. With this SPI example, we can use it as a starting point and sort of change stuff until we feel that we understand it properly. But yeah, it's still a little bit too fancy. We don't need the full duplex. But then again, maybe that actually makes it simpler, because when it is full duplex, you don't have to have separate read and write. Otherwise, I guess you need different programs for reading and writing data. Yeah, so actually, when we look at this, so and also the pin numbering here is confusing and yeah. What is PIO? Okay, so just a quick quick information about that. So on the Raspberry Pi Pico, there is a special block that allows you to run this sort of machine code on the GPIOs, which enables us to do extremely fast and low latency interactions with the outside world. If we're going to DIY a simplified version, we'll probably need an ordinary Pi Pico version with a budge for LED GPIO or whatever. Yes, I was thinking about that. So, okay, so actually let's tangent a little bit. Let's leave this stuff for a little while. So again, this is the PCB that is currently in production that, yeah, actually some people in the community have already also ordered. And this is the first, very, very first version, which I intended to just be for me. And I will need this to experiment and explore stuff. But yeah, people are, of course, free to produce them. So with this board is sort of, yeah, the very first step. So the USB is connected to the Pico, or RP2040, and the RP2040 is connected to the bus. And we have the IOs connected here. We could, of course, make a simplified version where we remove this module and replace that with a Pico instead. And in fact, I was thinking of doing that. So actually, should we just do that instead on the stream? So let's just drop the PSRAM, PIO stuff, because that's kind of, it requires a little bit too much brain, and I guess I'm not really there today. So, but PCBs are easier. So I guess we can just do that. Yeah, you're totally right, JTH, and I don't. Yeah, I don't mind. The problem I see with the Pico is there's limited flash. It's only 2 megabyte, and it's limited on GPIOs, but it might be enough to do interesting stuff anyway. J chiller up. Woo! All right, let's go. So, so that means that we have a challenge in front of us. We need to change branches. We didn't actually do much on the PSRAM stuff, but let's just save it anyway. Yeah, let's just keep it here. PSRAM. Yeah, I got both of them. Good. So now we're back at the develop branch. So now we have a versioning challenge. So currently I have this directory called PicoCart64-v1. And I was thinking of having sequential versioning, or like the semantic versioning, I guess, where you start with like 1.0.0, and when you make small changes, you update this one. Oh, sorry, maybe you don't see this on the stream. Let's just do like this. So you start here, and you do small changes, and then you make some big changes, and then you make some really big changes, and you do it like this. So I'm thinking version 2 will be like the actual fully featured super nice board, but this will sort of be a variant. It will not really be PicoCart. It will be like the PicoCart64v1 Pico or something, which will be a really confusing name. So I'm already regretting my choice in that. So what do we do? We have this here, and also, yeah, damn it. If we can close this down, I can close this. Yeah, I already pushed those changes. Did I? Maybe something that signifies its simplified nature. Yeah, I agree. So maybe simple. PicoCart64 simple. So let's go for that. PicoCart64 simple. And then let's copy. So actually, if anyone knows of a better way of you know, forking or copying you know, KiCad project, please let me know, because this is going to be a little bit tedious. Yeah, this is all fun. So I already used this kind of relative paths, so that's cool. Light. Or yeah, okay, yeah, light is good. Light is good. Let's go for that. Let's go for that. I like it. It's also short. So let's remove the Gerbers and the backups. Okay, is anything? That's good. Okay, so now we just need to rename some files. Now I'm mixing underscores with dashes, which I already regret, but a dash makes sense here. Or does it? I don't know. I already feel I have mixed feelings about this. Oh man, this better. Yes. It's funny how small decisions early on can cause so much headache later on. Yeah, let's just do this. And then we need to update the Vento. Yeah, you're right. But to be honest, it's kind of stupid because in the Pico V1 I'm not actually using a Pico. But yeah, it is what it is. Okay, but that is fine. But now we need to change these. And we need to call that light. And like that. Do it like this. Yeah. I think that was everything. So let's just start with a git add. Like so. Now we have a starting point, and then we can always revert back to this. I think it actually got so popular because of Pico usage, kind of riding on its publicity. Yeah, I suppose so too. But I mean, it is the RP2040, so, and people use the RP2040 and Pico interchangeably, which is unfortunate, myself included. But yeah, let's hop into KiCad. Where did I put it? Here, I guess. Yep, let's go. Yeah, just 1 second. Okay, so this is, as you can see, this is the light version. So here we're gonna simplify this a bit. We need to kill this one, and we're gonna kill. No, okay, let's. Okay, I didn't add that here. I remember I was adding the Pico stuff to that other thing. Yes, give me a second. I will dig up some files. Yeah, just 1 second. All right. Yeah, there we go. Okay. So this was the footprint and schematic. So just 1 second then. Come on. Yeah. So we want this one in symbols, and we want the 3D render here somewhere. Yeah, I know. I actually tried to use Wayland and Sway, but there was something that didn't work well. I think it was something with my dual monitors and 144 Hertz and stuff like that. I don't know. Something annoying. Okay, where do I put this then? Yeah. So I guess. Yeah. Okay, that should be it. And then we need to update the paths. Not that path, but there we go. So we do like this, and there we go. So now we have this thing. Now we need to sort of remap everything. Yeah, what is the easiest way to do this in the same way? Guess let's just create some space, and let's worry about the cleaning stuff up later. So we need this to be in sequence, but we're gonna put them on this side. Yeah. So we put these guys like so and like so. Here we go. So this would be easier if I just do like this. And then do this. And there we go. Done. Almost. Yeah, there we go. Yeah, and then we need some ground. Guess I can put that like so. Yep. Again, everything matches 0, 0, 1, 1, and so on, all the way up to 15. Yeah, perfect. Sorry for some motor sounds. Okay. This one already feels nice. We can put the debug pins here. Where did it go? Okay. So now we are a little bit on our way. Nice. We want these to be exactly like on the other project. Yeah. So then we're gonna press the X button. No, the Y button. There we go. So now we flipped it. So this is 16, 17, and so on. So just according to plan. There we go. And this one goes there. So this is actually exactly how I hooked it up with my flying wires. Then all right, I don't have to connect that. Or actually, maybe I have to. I don't know. It's connected to just a ground plane on the Pico. But I think the DRC will complain if I don't connect it. There we have another one. Okay. Okay, so run, what was that again? That's the reset. Right, and we want the reset actually. So let's move this. There. We don't need that one. We don't need that one. We don't need that one. The V bus is the 5 volt. In this case, I don't know how the Raspberry Pi Pico works if you give 3 volts to it. We need to do some research. We need a datasheet of the Raspberry Pi Pico. There we go. I need to know how power supply works. Can you power it with 3.3 volts only without USB? I don't care about power consumption right now. Okay, here. This is interesting. 4.5. Okay, thanks. Yeah, this is from the 5 volt USB versus PV bus voltage, right? Via U1. Okay. I already feel danger because, okay, just, foreshadowing. Let's say we connect stuff the way we think it works. Then people will make boards. They will solder down a Raspberry Pi Pico. They will plug it into their Nintendo 64, turn it on, and then connect a USB cable. What happens? Yeah. I have a bad feeling about that. So I want to make sure this is done correctly. Okay, so if USB port is the only power source, they can be shorted together to eliminate the short. Okay, that's interesting. If it's not going to be used, but we actually want it to be used, so we shouldn't read this. Or, I mean, no, exactly. We have an issue here. Like, people will connect the USB port to their computer, and people will connect the system to the N64 and power on the N64 in any order, like first N64 then USB, or first USB then N64. I'm sure, I mean, yeah, that is gonna happen. So we need to figure out what is a safe way to handle that. Okay, but that is fine. The simplest way to add a second power source to the Pico is to feed it into VSys via another Schottky diode. Okay, that is actually really simple. This will order the two voltages along the higher. Okay, that is actually really simple. And I also have a bunch of Schottkys at home or in the hackerspace. So, but this is now looking confusing again. I guess this is the, okay, so this is the external voltage. I see. So we should put it, we should have a Schottky. Yeah, let's put a big Schottky here. And not connect with this. Yeah, because we don't. Right. I'm thinking too much. This should go away. Because we have the USB connector on the Pico. I'm thinking too much. So we should just ignore VBus and then just do like they say. And then here we put the 3.3 volt from the N64. And we don't even need this. And we just use this. Wait a minute. We use the N64 VCC as a source here. And then we call this 3.3. Just no, or no, wait. Yes. No, yes. So this is the N64 3.3 volt source. So this is the N64 3.3 volt net. This is the 3.3 net, but that is also not good because we have the Schottky diode here. No, okay, that is incorrect. So we should use this as the 3.3 volt source. Yes, okay. So yeah, it's cursed to have this on this in this direction, but hear me out. Okay, let's think together. This is the external 3.3 volt. It is protected by the Schottky, so the 5 volt that may come here cannot go here. Good. This net will always be 3.3 volt because that's the 3.3 volt net of the Pico. So either it comes from the VSys, which will drop from 3.3 to 3.0-ish. Is that the problem? Is that a problem? What should... Any other fixed supply range in 2.3 volts to 5.5. Okay, this means that if we have 3.3 volt here, we have a Schottky here, this will drop some voltage, like 0.2, 0.3, something like that. So our input voltage here will be lower. It will be interesting to see what the 3.3 volt net becomes. So I could measure this using a multimeter and connect a Schottky diode and feed it with 3.3 volt here and just measure and see what we get. But I can also YOLO it and say it will probably be fine. But this will not be 3.3. This will be 3.0-ish. Everything is in the docs. Just read and don't. Okay. Sorry. And info. Okay, so that is what you mean with the MOSFET. Okay. The gate is controlled by BBus. Right. So there should be a PFET. Right. Okay. So what's the BSS84? It's a PFET. Yeah, okay. So it is. Okay. So yeah, let's add that back. Let's read everything. Right. Yeah, shouldn't you have like a pull to ground on the gate, I think? There they use this one. I mean, if they say it's a suitable one, then let's go for that one. Can you buy it? Uh, 2 million on order. Okay, so it's not in stock. Oh my god, look at these numbers. So you cannot buy it. You can buy it from LCSC. Is it pin compatible with the BSS84? Because I have a bunch of those. So we have gate, source, drain. Gate, source, drain. Yeah. So it's compatible. It's a SOT23, and I think this is a SOT23 too. Okay, which means that we can just use this one. We can use this one. It's the same pin out, same package. So let's continue reading then. Okay, so the gate should be connected to bus. Okay, let's put that here. You can use something like TPS21111A to switch between N64 and external power from USB. That sounds like a TI part. Ooh, fancy. Can you buy it? Kind of. But it feels a little bit overkill. If we can do with just the BSS84 or this one, then I think that is good enough. But thanks for the suggestion. It's something to keep in mind later on. Thanks for the follow. So I think I will go with this design. So yeah, and yeah, sorry for jumping to conclusions and stuff, but it's like I'm reading stuff and thinking at the same time. This is nicer. Yeah, we're not gonna use that one. So then yeah. BSS84 are hard to source. Really? Really? Because I think I mean, they are like basically free, and they are. I mean, this is good enough for me. So I think I will go with the BSS84. But yeah, I think we need a pull down. We just use a reference schematic. I was looking at like we can look at the what's it called again? The stamp. Yeah. So this is the inside of the stamp where there's a battery switch. So we can do, it's essentially the same thing here, but here you also have a Schottky in order to not backfeed, which I am slightly concerned with this design. No, right, it's a little bit different. But here you have the gate and the pull down on the gate. So I think we might want to have that too. But how do you draw that in a nice way? We can't. Oh god. So I guess you can do like. This is gonna look ugly however I do it. So we want this and we want. What the heck? Why is it being so ugly? Yeah. Yeah. Maybe I should turn it. Yeah. There we go. Okay, and then this one, that's gonna be ugly anyway, but yeah. So just double checking. Are we doing the right thing here? We have the VCC on the source, I guess. And we look at the reference here. Yeah. Now it looks a little bit more like this. So we have our voltage source. The gate goes to VBus. Yes. And then we have VSys, which is here. Yes. And then we have a pull down resistor here of 100K, so that the gate will not be, yeah, it's good design practice to do that from what I've heard. Thanks for the follow. Yeah, so now we are switching correctly and we don't lose any voltage because we don't use the Schottky diode. So great. And also thanks for nagging at me, JTH. Thanks. I'm, yeah, I tend to do stuff before reading everything. Bad habit. So we have 3 GPIOs left. So let's just call them PIO 26. And like so, and not text. What am I doing? Right, and then we have these guys. This is our IOs. So I'm just gonna make a pin header, I guess. Yeah. We don't need the boot button, right? Because that is on the Pico. Yeah. And we can't really do anything about this. We could. So now we have to. I mean, I could just put the solder jumpers for the rest of the signals. But yeah, one signal that we wanted was the pin 44. So let's add that. N64. Interrupt. So we want that to be exposed here somewhere. These, yeah, we're kind of limited. We only have these. So the question is, how do we want to hook this up? First of all, these are just the extra solder jumper thingies. We could have something like, you know, something like this. So you have two options per GPIO. So either you solder this one or you solder that one, but not both. I could also put, you know, jumpers, ordinary jumpers, like not solder jumpers, because that might be more DIY friendly, to be honest, because this requires you to use, you know, soldering and wick stuff, which maybe not everybody has. Maybe break out all the cartridge signals and we can add some field for customization. Yeah. Oh, you mean all signals? Like all? Or only these guys? Because if we are doing everything, then it's gonna be a mess to route. I don't really have the energy to do that. Because I think what we have here is good in terms of, or maybe, I mean, we could break out these perhaps. They can be good to have broken out, to be honest. So let's do that. That's not bad. But we can skip the, yeah, all that are supposedly used by N64. Do you mean including the address data? Because that's a lot of pins. So you mean basically we're gonna get a just have points for soldering to. If we want soldering points, we can put test points for all. I mean, outside of the module, we could have like a test point, and like make the pads like wider so that it's easy to solder to. So you can solder a wire to this, solder a wire here. Do you follow? Is it a decent idea? So that the footprint has like longer pads. So you get like an indirect test pad for each pin. Because then I don't have to route to a connector, because that's actually, yeah, can get a little bit messy. But yeah, we can get rid of these. I think that's a good compromise. Yeah, because I think then we can finish this board today, and people who are like, oh, but I want to use a Pico, I don't want to buy a stamp, can do that. And of course, this board is super untested, and it will also make people sad because you can only have 2 megabytes on the flash, and you cannot have an SD card with just 3 GPIOs. I mean, you can technically solder the fourth from the LED. Let's look at a Raspberry Pi Pico high resolution photo. Oh, thanks. Copy link address. You want like a project area on the board. That's a good idea. That's not bad. Yeah, we can add that. Like nothing is connected. It's just soldering areas and through hole. Yeah. And we could even have like a column which is ground and a column here which is VCC. That is absolutely no problem. And we can also make this board 2 layers to make it like even more like super cheap and easy to make. Yeah, it's a really good idea. Let's do that. But yeah, let's just here we go. Okay, so the LED is it DIY friendly to tell people to solder to this pad and solder like a wire from here to here? Like we have a test pad that says connect to LED cathode or anode, whatever it is. I think GTH wants the cartridge signals accessible in such a project area. Yeah, I don't want to make that. I mean, I could, but it's work and we are not gonna get done today. So yeah, so let's just call this 25 and make like a test point and have that here. Just a field to place custom components. Okay, thank you. That I can do, no problem. No problem. Yeah. What about not changing the schematic at all and just do a through hole thingy along the track in the PCB design? Let me try to understand what you mean. You mean just empty through hole pads? Like there's nothing connected to the pads. They are just in an array or like a pattern. Because that I can do. That is super simple. So I guess these should be accessible in that somehow so that people can easily solder to it. So I guess what we can do, yeah, let's just finish this up a little bit. So this one is the, okay, let's add a text here. Router orders to LED anode. This looks like a ground plane, so that is the cathode, and that is the anode. And this is the current limiter. So you can solder here is the best point. The second best point is here or here. But this is probably the best point. Because yeah, this looks like it's the ground plane. And the ground plane goes to this point. So that's the cathode, the anode. But there's something here as well. I mean, I know this is open source. We can look at it, but I don't feel like it. We can, but yeah, tell people to either solder here or here, there, I guess. Anyway, then we can solve that later. Oh, thank you. Copy link address. Let's go to Pin 25. LED. Okay. Okay, so there's a test point 5. Okay. But we want this actually. But yeah, I mean, it's not the end of the world to be 500 ohm. But okay, yeah. Let's write for R3. No, sorry, R3. So, I think this is pretty good enough. And then we need a connector 1x01x04. And we put that here. And then we have this stuff, which we want to have in the project area. So the question is, what is a good way in KiCad to represent this whole array stuff? I mean, we could make a footprint, which is probably the easiest. And then we just, yeah, let's do that. Okay, so we're gonna make a custom footprint. So it's actually been a while since I did that. There we go. Okay. So we can go from 1x. No, actually, let's just do it ourselves. Or no, let's go from this one. Why is it being weird? I should be able to find like the ordinary connectors. Where is it though? Pin handler. There we go. This one, and we take like this one. Yeah, and then we just copy and paste it. So save in library. We should have a library for our stuff. Have that one. This is always a little bit annoying. I don't really feel to make a. Guess we're gonna make a new library then. I wish there was an option to be like save in new library, but now I have to do new library. Let's see, project, and put it in symbols. I call this connection project area. How many do we want? GTH, do you have any? Oh, we can decide that later. We can always change this later on. I'm just gonna remove some stuff that I don't really care about here. The whole keep out stuff doesn't really matter. So if we want it to be like 8 by 8, just actually, yeah. So we could have a few different pins. So we could have like ground on one side, project area in the middle, and then so. All right, I'm already. This one should then be 2. And I'm just gonna ignore the DRC rules that says, oh my god, it's not connected. Actually, visually, this doesn't make sense. So let's think a little bit more. Let's do so the square ones, that's ground. Okay. And then you have like a bunch of round ones, which are your project area. And then we can have VCC in the bottom or something. So we could make, actually rotate it like 45 degrees. We call this like 3. And in contrast to this will actually be its own net. So we will connect all of these together. I guess we can make a, I don't know. I don't know. Maybe it was stupid to make them. But I want people to see that they are different. Maybe there we go. Now you see a different, like this is the sharp one, that's ground, and this is the rounded one, that's VCC, for example. I think that could work. So now we have a project area like this, and if we want it to be wider, we can very easily just extend it, no problem. Like so, and like so. Yep, there we go. Fuck. Didn't I just create one? Okay. There we go. So, and then we do it like this, project area. Okay, I don't have a symbol for it, so I have to do a connector like this. Yeah, and this is the project area. So we have VCC or 3.3 volt. Yeah, I guess in the top then. And then not connected and ground. And then we do the thingy. Oh. There we go. Okay, there we go. And now we press the magic button, F8, and say delete. Here we have our project area. And we have to reroute everything. It is how it is. Yeah. Yeah. Oops. But just to give an idea of how it will look. Yeah, here you have it. Oh, right. The 3D model. That's obviously wrong. But yeah, then you have like the... I should change those so the... Footprint editor. Yeah, there we go. Maybe... Oh, right. Should actually not have a pad here. Yeah. Then it doesn't become a net. Because we don't want it to become a net, because then KiCad becomes confused. Or it tells us to connect it, because it, should. And then this one should be 2. There we go. And now that doesn't make sense. We need a 2 connector. Yeah. So now we only have 2 nets, the power and ground, which is correct. Yeah. Yeah, I think the size of the test pad should be good enough. Should be easy to solder for people. And also, it shouldn't really rip. Like if you have 2 small test pads that people are actually supposed to solder to, if you make them too small, then it's very easy to rip the pads. You know what? Now that I think about it, that should be a connector. Yeah, let's do a 1-pin connector instead, because people have a tendency of being somewhat not so careful when soldering. I mean, if you're DIY and you really don't understand, I mean, if you don't have the experience of PCBs and how it works, then having a test pad like this is dangerous. It's better to have a hole, so then people can connect the pin there, and you can have a jumper wire and whatnot. So makes sense. Make it through hole. Yeah, exactly. That is what I'm doing. So perform. What am I doing? There we go. Bin header vertical. Yeah. Yeah. So this will be much easier to solder to. It's just a simple hole. Yep. So I will have to clean up the board a bit. So yeah, there's a lot of stuff we can just remove. I know there's a feature to remove like unconnected tracks, but I think I might want to keep some of the fan out intact. Yeah, most of the stuff should go. And like all the inner layer stuff, yeah, there's just a bunch of BS essentially. Here we have some tracks which we should remove. Yeah, because we don't have this layer. This is the backside. Let's just clean up some tracks. Yeah, I honestly don't know how much makes sense to keep. And we need to clean up the select screen. We might want to keep those. And this is PicoCart*SILite. And we don't have those. We do have these, and we could actually have that in a decent place. Oh. We can move that later on. Doesn't really matter. We have some. There we go. Okay. Getting somewhere. Okay, so I guess it's time to add the Pico as well, right? There we go. Oh, okay. Guess I will need to do the full routing after all. This is gonna be a mess. So first of all, we need to decide on a few things. Where do we want stuff? So I think it would make sense to keep you know, keep the connector in the top left corner, because that's how most cards do it, but we can't really do that. Okay, so now it's time to make a decision. Where should we put the Pico? Where we put the Pico will, you know, decide how difficult the routing will be, and where the USB connector will be. So essentially, if we put it here in the smack middle, connector on top. Oh, yeah, that's really good feedback. Question is if we can. Yeah. In the middle. Yeah, where is smack middle? It's the here. So it's pin 38 middle. So, so. Okay. But yeah, we have a problem. We can't really do this. It will be we can't really do this. I mean, having stuff so close to the connector. Wait a minute, let me just update the 3D model. 60 millimeters hard limit. I mean, yeah. Holy crap. Is that a huge model? It is 5 megabyte. Okay. So I guess we have to wait. Yeah, this 3D model was very large. Damn. Maybe it crashed. One more time. Here we go. Okay, so here you see, you know, it is like technically possible to do this. And this, I mean, to be honest, I don't know if people will put this in a case. Maybe some people will, I guess. But yeah, most cases actually have some free space up here. So maybe we could, I mean, it's gonna look weird as heck. We could make it a little bit higher here. I mean, I get it, but it also looks really, yeah, I mean, this is a little bit scary. But yeah, not having the connector close to an edge is of course a problem. You won't be able to put it in a shell properly. But routing wise, I would like have it like so. And like from a debug or like user point of view, yeah, sure, it's gonna look a little bit weird, but you can connect your USB cable there. I don't know. Okay, what's the reason for not just having it horizontally aligned? Yeah, so ideally, you want the USB connector to be here, so that you know, it's close to an edge. But the issue is that you know, the PCB is not big enough, and we don't really have control over the PCB layout because that is dictated by the cases. No, but it's good feedback. It's a good suggestion. So this is kind of what I want to do, but we cannot do. And JTH was suggesting putting it in the smack middle and having the like so, and having the USB connector pointing upwards. There you go. So I mean, this is technically possible, I suppose. I guess we should align it so it doesn't stick out too much. But the problem is then that we have these signals. I mean, it's possible, but it's going to be a bit of a drag to route. But I guess we can do it. So if this really is what we want to do, then yes, sure, we can try, and we can probably solve it. But I'm also afraid of, you know, this, like the connector. You know what? Let me take a photo of an N64 with the breakout board connected. Just give me a second. Sorry for the delay. So I've taken a few photos. Just solder the Pico to a rail of 0.1 headers. Lift the Pico from the board slightly. There should be no problems. And height. Yeah, I mean, I have a few empty cartridges here that I could measure Most cartridges come with these metal cases as well, where how thick is half of the shell. So okay, maybe I should just turn on the camera. It's gonna look like crap because of my bad lighting, but yeah, I don't know really. So there you go. So here's one of those, AliExpress cartridges. I would prefer to buy these guys without any logo, to be honest. Just okay, some LED strip already. Yeah, I should. Okay, so this is how it looks inside. Sorry about the focus, but I don't dare to open the settings, actually. Okay, slightly better. Okay, so this is how it looks inside. You have this sort of metal can, which is also kind of annoying because, as you can see, it's it cuts the board in half. So if you get exactly this case, you need to modify this and sort of bend it or cut it along this line here. But yeah, here you have the height more or less. So I can measure, let's see here. So I can measure this height and this height. So the high height is 9 millimeters and the low height is 7 millimeters. Yeah, so 7 millimeter and 9 millimeter. And on the bottom thingy, this looks like this. So this height here it's almost 9 millimeter, like 8.4 millimeters. So we have 7, 8.4, and 9 millimeters. So if we go by the lowest one, we have 7 millimeters. But that is like the whole package. So I guess it's like divided by... No, actually it's mounted like... I don't know if you can see really, but... So you have this here. And this little thingy presses against the PCB on the back side, or I guess front side. For the next iteration, it would be nice to interface the RP2040 chip directly. Yes, and that is definitely in the pipeline. But that also means that it's not at all DIY friendly, because then you need QFN soldering, which some people can do, but most people cannot. So that is why the stamp and Pico is sort of nice to use. But yeah, I don't know. But yeah, again, we also have this, like if you look at the this shape here, we have some extra millimeters that we could use. So Pico 1, Pico 2 revision used the stamps. No, yeah, so the thing is, they don't have to. It's only a concept. So the concept was more like, we have these two RP2040s that are connected somehow. So I was thinking of, which is also over designing in my head, but we could do two variants, like a DIY friendly using stamps and production board using QFN. So that people who are like, I want to build my own board and I want it now and I want to control everything, but I cannot solder QFN. Sure, go ahead. But it will be a little bit pricier, of course, because the stamps are $12-ish in that price range. But it is possible to do. Most parts, I mean, the only parts that will be hard to solder is the USB connector. It's a little bit fine pitched, but you can do it. Then you have the QFN. That's it. And the SD card reader can also be a little bit complicated to solder, but doable. So yeah, going back here, what do we want to do then? So, oh right, I took a photo. Can you put Breakout PCB into shell and see how it fits? Yes, 1 second. So I took a few photos of my N64 as well. But yeah, let's see here. This is the right direction. Yeah, 1 second. There you go. Let me just fix the focus. Okay, autofocus mode didn't really work. You know what? I'm just gonna take a photo instead. It will look much better. Yeah, something is a little bit, I mean, this metal thing kind of messes up everything. So these metal shields need to be sort of modified. But just to get the dimensions right, you can do like this. Good enough. I suppose Breakout has the same dimensions as the current board. Yes, that is correct. That is correct. So, uploading photos. Okay. So, let me just do like this. So what we're looking at here is a naked N64, and we're looking at the front. Oh, sure. I need to change. There we go. So what we're looking at here is the Breakout board connected to the N64 port on a naked N64. So there is no plastic. If there is no hard limits on 60mm from production side, next more expensive tier of PCB dimensions, for example, we can go with a slight protrusion in the middle. Yeah. And here it is connected in an actual N64. But again, this is the naked PCB. When you have the cartridge, you sort of push these flaps down. So the important picture is this one, that you see the numbers here. You see this edge here. So this edge is more or less the hard limit, the really, really you really shouldn't go below this edge. So just to compare it with here, so these numbers, like this whole area is no-go. This is a keep out area. You cannot do anything here. Because if you look at this picture, you see the numbers here. You see this edge. Yeah. Here it is, and here it is from the other side. Yeah. So there you have it. Right now we're too close, that's correct. And okay, sorry for the blurry picture, but it's slightly better than my webcam. But as you can see, there's a lot of space here. So we could make a funky looking PCB with like a thingy that goes up here. So that is one possibility. I guess the easiest one, we can just make a simple shape here. From 20, we go up here a bit, and then we just do like a square or a rectangle, like so. Yeah. So we need to take a decision. But yeah, we could essentially, if we go to the edge cuts, yeah, and then what did I say again? Yeah, around the between 20 and 5, so or between 45 and 30, yeah, so between these two lines. Let's just make some markings. So here we go. And I want to just make a line. Yeah, so here. And then we have this layer on number 30. Yeah. So we can extend the board a bit here. So exactly how much can we extend it? Let me measure. So I think 6 millimeters is fine. Yeah, 6 millimeters should be fine. That is something we could do. I think that's a fine suggestion, but getting the USB connector flush with the bent top edge of the cartridge is going to be annoying. Yeah, that is going to be extremely annoying for multiple reasons. So, no. So again, sorry for the focus. Let's see if it can fix itself. You know, this plastic is pretty thick. And even if you like cut it open here, you can do that. That is a good point, that we can do a 3D print. That is true. That is true. And maybe, yeah, it becomes really DIY then, which is nice. I mean, we get like an open cartridge, which is not a Nintendo derivative and so on, which is cool. Yeah, this is pretty, like, it's quite a lot of plastic. So you have this, and then the thickness of the shell is pretty significant. Low focus. Yeah. Yeah, and this is only the first prototype anyways. I guess we all want to get the PSRAM and 2x RP2040. Yeah, I suppose in the long run, yes, for sure. But then there was also the use case of, you know, homebrew people who wants to deliver their homebrew, and that is like definitely possible with just a Pico, and you put the homebrew on the flash, and off you go, you're done. If you don't care about, you know, save states, and because we haven't really implemented any of that, but that could be a quite cool thing. Like if you're a homebrew developer and like you just buy a Pico, you get one of these breakout boards, you just solder it down, bam. That's all you need. But if we're gonna 3D print, there's not a lot of reason to keep the vertical alignment of the Pico anymore. But yeah, even if we do a horizontal one, yeah, I mean, then we could basically ignore a lot of these constraints, I guess. I guess we still need some kind of notch, which makes sense to have. But we could, for example, make this edge higher, make the whole cartridge a little bit higher. But then some people will complain that, oh my god, it doesn't look like a real cart and so on. So I don't know. Yeah. Are there different cartridge forms among N64 library? That is a really good point, and I don't know. I believe not, but I don't know. But I saw a photo of some collection, and most of the cards looked exactly the same. Some were in different colors. The connector on the underside. What? You mean? I guess you were joking, but I don't follow. We could make this into a dock. Oh. Well, that's overthinking a bit. Okay. So just being lazy, the best solution for me is like putting it here, but then we also want to have the project area somewhere. So we could put it like here, for example. That is not that bad. You get like in line here, and the cable would, you know, you might be able to open up the cartridge on the side. If I put it there, then I could actually put it here. Something like this, but then it looks asymmetrical and like kind of odd. Oh, no, the 3D died again. So if it looks like this, and you look at it from a side, and it's like, oh, there's a USB connector, and okay, it's a little bit in. But if you think about it, let me just give you some reality check of this size. Like this looks huge on the PC, but let's just go full camera here. Oh, test point 2 and test point 3. That is interesting. Yo. That is interesting. Which is it? These two test points? Now let me check on the. If horizontal, you could poke the USB out the side. Yeah, the problem is a few things. Like if I put it like really close to here, then these will be annoying to route. And if I put it like here, then this goes outside of the board. So this is more or less, I mean, I could technically do like this, and then I can modify. I mean, it will be really annoying to solder down for people, but like this is like technically possible. I suppose. It sticks out a little bit. That's not good. So I guess we need... Oh, shit. KiCad is not very nice to me when you have big symbols or footprints, I mean. Okay. So it's actually this line. Okay. So I guess there you go. So assuming the 3D model is correct, okay, we could move it there. Okay, this is more or less the best I can do. I made, 1 second. All right, we have that notch too. Yeah, that is not gonna fly. So there we go. So yeah, here we go. Now we are not violating any of those rules. Yeah, so we're not sticking out of the notch. Yep. And from this side, this is how it looks. The USB connector is basically flush with the edge. Sorry for the wonky camera. I'm just trying to get a better view here. But yeah, this is the absolutely best you... Oh, fuck, sorry. But yeah, anyway, here we go. Now I moved it so it's like as close as possible to the edge. We're not sticking out of the notch areas. That is fine. And on the top side, we are like, yeah, this is violating the design rules, but which is the edge cut? Yeah, here. From here to basically down here is 1.5 millimeters, which is like a lot. So it's possible that this area, like down here, will not be properly made by the PCB manufacturer, but down here is no problem. So yeah, this is definitely fine. So maybe this is it. Maybe this is how we should do it. So what do you think? Is this acceptable? Having it like this. I mean, I would have preferred to be able to put the flexi pins here as well, because of multiple reasons. Flexi pins, if you're not aware, it's the one that I used on the other design, but it makes it possible to easily swap out the module. Okay, I don't have it open here. Now the notch is too close. What do you mean? It should be fine. I mean, we are not sticking outside of the notch. The connector is slightly outside of the PCB. I mean, this is, if we look at the case again, yeah, this is, 1 second. Right, so the case is gonna, the case will not like this. The USB connector needs to be flush with the PCB edge, otherwise it's gonna squeak. Yeah, but actually, yeah, I foresee that it will be a pain to route. Yeah, I mean, that's kind of, I thought this was, you know, I was kind of hoping this to be like a, okay, fine, it's the DIY We're just gonna make it easy, put it in the middle, smack, bam, done. But this, I mean, this looks narrow, but there's actually a lot of room to route. Put the signals here in between. So I don't think this is gonna be hard. That hard. I can do it. And then we can put the project area over here. And actually, we don't need the debug header because you have this. You have the debug header here. I'm gonna remove that, to be honest. Let's just remove that. Yeah. This is for the project area. And we also need some IOs for these. So let's see how many are there. Yeah. Project area is flexible. No, of course. So I just made it 8x8 to have a starting point. So we can fix that later. So I just need to fix the footprints. Bloop. And we put this one. And this one. No, not socket. Header. And F8. Do your magic. Right. Oh no, I picked the wrong one. Crap. So you could do something like you align these. But yeah, it's a little bit dangerous to have them too close because we have the power rails here. You have this one, you could have it like here. Yeah. So what do you say? Should I make this having 8, like 10 high? And then we can have these signals here. And then we need some silk screen, which is no problem. We can do that. I mean, I start to like this design. It's not bad. Oh, copy link. Yo, what is happening here? Okay, so you want this. I see. Yeah. But it's good to keep in mind from the beginning, like, you know, you have these are the bus signals and these are the GPIOs. I guess maybe we could move them like so or something. Doesn't really matter, but right. Finally. Okay, cool, cool. Yeah. So now we have a placeholder there. We want this connector to be like close to the LED, which I think was around here. Yeah, there. Right. So the user solders a wire from here to here if needed. Can we do this on 2 layers? What do you think? Yeah, and then I'm just gonna do a ground fill on both layers and call it a day. Yeah, I think I'm gonna reset this whole chunk. LED test point is on underside as well. Oh, right. Oh, you mean we could put the... yeah. Okay. Here we go. So it's this one here. So yeah, it's gonna be janky as heck if we just put like a pad there and you put like a tiny solder blob there and it might stick, it might not stick, you know. Yeah, because normal people, like DIY people, will not reflow the board onto the other board. Yeah, it's an idea, but yeah. Oh, actually, are these the test points? They might actually be. Yeah. That is actually... Oh, you know what? No. Yeah, exactly. I was just thinking about through hole. That is... No. It's not that bad. Because if you just use enough solder and heat and have patience, you should be able to do it, and put some flux before. I mean, we could actually put a pad there. So let's actually do that and have that as a sort of pro option. If you feel like it, you can do it. But that also requires you to solder down the... Actually, this already requires you to solder it down. Or you could put through, yeah, headers. We can do it. That's fine. So yeah. Where did it go? Oh, maybe I didn't annotate it. No, I did. Ah, here we go. Okay, not bad. Not bad at all. So yeah, it's almost 11 o'clock and we haven't even started the routing, but I have some hope that the routing will not be that difficult because yeah, I think we can do it. Okay, now it just crashed. Okay. Okay, so they are here. Yeah, I'm gonna skip that. So I think this is a good starting point. Let's put this one somewhere close. Oh my god, it's over there. So maybe we can put it close to the VCC stuff. All right, before we continue, we should change the board to 2 layers. Stack up. Stack up. There we go. No. There we go. Yep. Bye-bye. And then let's just be super lazy. And okay. Oh, you can actually have multiple layers. Didn't know that. So now we have a filled copper area with ground on both sides, which is pretty standard for 2-layer boards. Oh, we have the boot select stuff, but the boot select is on the board itself, so we don't have to. This button is boot select. But thanks. Oh, so GPIO 23 is also pulled out. Wait a minute. Do we have 23? We did not. Okay, so that is actually an extra GPIO. Test point 456. Okay, so 4 is actually GPIO 23 then. Okay, let's at least add that as an option then. I'm gonna copy this. Okay. Okay. 3D is updating. It's a bit slow. So yeah, there we got that one. Really don't like the behavior. Oh. Okay. That should be good enough. Okay, then we have this one, which we should place somewhere. It have to be so damn close. We have space. Right. Okay, so before we start routing too much, let us decide on a few things first. So, yeah, it's should we make the project area bigger? Yeah, we can expand it further down, I guess. Because once we start routing, we might have some stuff here going diagonally like this, and so it might be better to just make it bigger from the start. It would have been nice to have the silk screen, like being able to explain what these different IOs are without people having to look at the schematic and PCB thing. So one way to do that is to have the signals oriented differently. So you can have the text on this side. Like having it like so. I don't know. I don't usually do this, so I'm kind of not used to it. But I guess we want to put it like as far out as possible. And because since it's through hole, we cannot, what is it called again? We can't put silk screen like on the back because there's also through hole stuff. But we could of course have numbers on them, but that doesn't really help. We could have the text here, but then people might get confused. Yeah, I think that is actually the best way. So if we have it in this direction, let's go back here. So if we have it like this, we can have a guide that explains the pins like this, but they are like 90 degrees wrong. So you have to map them, or we make like arrows. I don't know. I honestly don't know. But yeah, let's just keep it there. So I just need a quick break. I'll be back really soon. Just 1 second. All right, I'm back. SMPS control. Okay. Where was it? I don't think we need to mess with that. Aha. Right. So GPIO 23, we cannot just use that. I see. So I guess we skip that one then. Why is it not recommended? I guess because the LED draws current and so on. Yeah, but let's not use this one then, because I guess the power, it will power down the unit and stuff. So let's kill that. But wait a minute, 23. So what happened after the break? Just nothing really. I removed the test point because of the SMPS. So if I understand it correctly, if you start messing with this, the unit will shut down. Because it said here, driving high the SMPS mode pin, force the power supply into PWM mode, can greatly reduce the ripple. Yeah. Okay. Okay, so that is GPIO 24. But we were talking about GPIO 23. That is here, right? So that goes to the PS, whatever that means. Power shutdown, I think. Power save, right. When PS is low, the regulator is in pulse frequency modulation mode, okay? Okay. So if you use this GPIO as sort of, I don't know, SPI, the power supply will probably not be happy if you start sending 1 megahertz on that pin. So yeah, let's not use it. So, okay, so what did we do? We did some routing. Guess it's time to do some more routing. So how does it look? It looks like this. Yeah, so my idea with these connectors was to put the text on this side, and maybe on this side you have GPIO blah 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 blah, and you have the power and the ground, and then the text for these will be sort of on this side, but with like arrows up here. I think that makes most sense, because I cannot really fit both text in a decent way otherwise. So I guess it's routing time. It's routing time. So yeah. What kind of design rules do I have? We have 8 mils. Yeah, that's perfect. That works at any fab everywhere. So we can just do like this. Actually, we don't need to connect those pins. Yeah, I mean, it will be a design rule violation, or like a bug, that these two are not connected, but it doesn't matter because they're connected on the PCB. But yeah, it's still a net. A net is a net. It's never good to sort of mess with that. Okay, so there we go. Now they are connected. Guess I should actually go by the top row first and just sort of route this. Oh, this is power. Oh, that is also annoying. That power goes here. You know, this is gonna be more difficult than I thought. Because, yeah. So let's do the power first. And for power, I want to have a better trace. Yeah. These actually keep out areas? Why? Okay, maybe because it's going to be soldered down, like flat onto the PCB. Okay, that makes sense actually. So I was thinking of something like this, that we route the power like so. I don't know. And then we do the same with the second power thingy. We just cannot really do this. Okay. I foresee that it will be a pain to route. You have been warned. You're not wrong. I really don't want to have a via on the power, and I really don't want to do this. Oh my god. Ugh. Okay, so how do we do this then? Oh, because we could actually Yeah, I want to have this on one layer though. I know that I can use both layers, but I don't want to cut through everything on both layers. That's why middle design is way better. Yep. Or maybe put the Pico on the other side of the PCB, then power will be facing down. That is a very valid point. I might actually do that. Yeah, let's do that. Because power is important and I shouldn't compromise on that. That is like the important first step, I would say. So yeah, let's move that here and then do like this. Boop. And then let's do this whole experiment one more time. Where we do like so. Doesn't stick out, looks good. And yeah, we could actually move it down a few millimeters. Actually, there's no need to have it so damn close to the edge. We could have it like, I don't know, here. So then that means that we could route on this side as well. That could actually help us a lot. Let me just select the test point as well, and this one. You can mirror the design and put USB on the right. Yeah. I'm thinking here of the USB connector, how low we want it to be. Like as low as possible is nice, but we should probably have some margin. Like if it's not too close to the edge, micro USB is hardly usable. I mean, yeah, I see what you mean. Wait a minute, I have a Pico here. How does it actually look? Oh yeah, the plastic thing goes down. You're right. Okay, actually, you know what? Let me turn on the camera again. Here we go. So, okay, this is gonna be a mess. Okay, let's do like so. Okay. Yeah, you don't see a lot, but I'm just gonna measure something. So on this particular connector, we have, on this cable, we have 3.5 millimeter between the PCB edge and the plastic. Like I know the camera sucks and I'm far away, but I'm measuring the distance between the plastic notch where that starts and the edge of the PCB. And that is 3.5 millimeters on this particular cable. And some cables are deeper than others, and so on. So yeah, that will be a limiting issue. That was a really good point because I totally forgot about that. I've been casing my Pico. Oh, okay. So let's just measure here. So if we go from the edge to, that is 2.6 millimeters. That is honestly doable in this particular, with this particular cable. I'm sure there are cables that are way more not so nice to use. In fact, I have a different cable here, which I'm gonna test with. Let me just fetch another Oh, I have one here. Right. So yeah, I have a different cable, and yeah, you're right, it's gonna suck. Yeah, I mean, this cable is okay. This is also 3.5 millimeters, 3.6 actually. So I know it was really hard to see on the camera, but I'm measuring, or maybe I just disconnect this cable. Yeah, let's go. Okay, so let's go camera again. So you see this little gap. Come on, autofocus. There you go. So with this particular cable, there is a gap that gives me like a, yeah, some room, and that distance is yeah, like this distance. And that is 3.5 millimeters with this particular cable, which I understand is not gonna be like a fact for every cable, but that, yeah, that would enable this. You know what? Oh, we could actually do a cutout in the PCB here, and then put a USB connector on the other side, but that's gonna be janky as heck. My idea was we make a cutout in the PCB so that people can solder to the test pads easily, and then from those test pads they solder it to a USB connector, which is you know, goes on the back side. I don't know, but that's gonna be janky as hell. Also, I'm not sure why we have these holes here. So if I look at the Raspberry Pi, there is no reason for those holes. There is really no reason for those holes. You know, starting the camera again. Oh, sorry, the camera was on. So let me just kill a window here. Here we go. So yeah, if you have a look at the camera, you see the board is flat, and by the USB connector there are the test pads. So I really don't understand why we have these cutouts. So I believe that is like a bug in the footprint that we borrowed. So honestly, I'm gonna fix that, or like change it, because I don't like it. I don't agree with it. So we're gonna do edit, open in footprint editor, and we are gonna just delete that. But I mean, delete the holes, I would say, because we don't want holes. We want, because they don't actually. Okay, I guess those are the ground. Yeah. Okay, for the connector, but yeah, there's no reason for us to have them as actual holes. So we could change them into something else. But they're actually only on the mask layer. Oh, okay. But why were they holes then? Oh, no, okay. There we go. SMD, and SMD. There we go. Micro USB jack has height. You'll need a gaping hole at the side of the case to fit it in. Yeah. I guess this is, it's important to get this right from the beginning because it's going to be a total pain in the to fix later. Sorry. But yeah, from what I understand, this 3D model is actually pretty accurate. And this little notchy thing here, it does actually only go like, it doesn't actually touch the base PCB, so that's fine. But yeah, the main issue is this notch here, which if we block it, it will be very hard to use in a cartridge, like more or less impossible. And having it like this makes it difficult to use. We could make a cutout in the PCB. Why didn't we do that? Yeah, let's just make a cutout in the PCB. Why didn't we think about that before? Like if I just make a notch here so that you can access the connector. Micro USB overhang is around 1.85 millimeter from Pico edge. Also micro USB jack has height. You need gaping hole at the end. Micro USB overhang is 1.85. Yeah. So, yeah, okay, I see. I'm just not paying attention. I'm sorry. So let's fix that then. So let's go to the drawing and wow. Okay. And now we can do that stuff. I'm just gonna so there's so much that has changed in KiCad. I don't know how to change the size of a line. Maybe I should just create corners. Yeah, let's do that instead. Okay. And also it's kind of almost the same color. Okay, but yeah, let's create corner. Thanks for the follow. Also, pads that you fixed to SMDs are actually through a hole on the real Pico. They're not filled and flush. They are not filled and flushed with the board. Yeah, exactly. That is what I mean. So because they are not flush, I mean, because they are flush with the board, there is no reason for us to have holes there. But I suppose it is okay. I get it now, and it is the more correct thing to do to have holes there, because there could be some production run which has more solder, which makes it sort of bulge out here so that it won't be flush with the PCB. I understand now. I was wrong, and I get it. But yeah, let's just make the cutout here, and it should be fine. I just didn't. Okay, so now I just want to understand how this strange program works. Because I used to just be able to press insert and I get like a point. But no. Okay, so I'm just gonna go old school and just yeah, the grid is all messed up in this project now. There we go. Okay, so 1 millimeter in, and then we do another round corner. Okay. And then we do a line. Oh. No. Because this whole project is based on this very specific shape, the grid is sort of not helping. So everything is like off grid. Because usually in my PCB designs, I'm super careful about the grid because it makes everything so much nicer. Yeah, I really can't do this. I guess the problem was this one. Okay, let's just go back here. So choose a decent one. There we go. We make this line 1 millimeter exactly. Okay, let's make another. This is extremely frustrating to work with because it doesn't really fit anymore. Because usually, oh, now I see what the issue is. So back in the day, here we go. Here we go. Yeah, so that was what confused me was that you could actually set the anchor point like on the line, but I'm used to having it in the center of the circle, arc circle. So that's why everything got super messed up. Okay, so how far in do we want it? I think going all the way to the PCB edge is good. And then 1 millimeter from here, I guess. So like that. And then we just right. So we want it there. Oh. Cool. Yeah, I'm sorry, this must be a little bit painful to watch when I'm just failing at using KiCad, but yeah, it is how it is. So how do we make this symmetrical? That's roughly 0.6, okay. So we want here. Okay. I need to sleep now. Okay, thanks so much for the super educational stream. Learning lots. Can't wait to get my hands on this board. Don't miss them all. All right, cool. Nice of you to join. Nice. See you next time. Okay, now it looks like this. So finally the edge routing has been fixed. So we now get this little cutout, and this notch is still there. And it should, I mean, I'm not a mechanical engineer, but this is probably big enough to be mechanically okay. And we have these smooth lines going here, the sharp lines here for the thingy, the notch. And And looking closely, we see that only the USB thingy goes through here. There could be USB connectors now that I think about it, or USB cables that are wider. I guess I'm gonna measure mine, and of course that is not gonna be a gold standard, but it is 1.05 millimeters across. So from there to there, 1.05. So let's see how much space we have here. So from this center line to this, we have 8.6. That is not enough. We don't know why the notch is there in the first place. Well, I can show you on the camera. So the notch is here. So I'm pretty sure that this notch thing is the Nintendo standard, like the what's it called again? Yeah, if you look at other original game cartridges, they are using this sort of shell design. But we still have like quite a lot of budget here, so what we could do is to just move everything up a little bit and have like 1.2 millimeters here, 1.2 millimeters. That would probably be good enough. So if we just measure from here to here, we have delta y is 8.6. So let's say we add 2 millimeters. So we just do like this, and delta y 2 millimeters. Oh, holy crap, that is a lot. Do we have that much budget? We actually do. It's gonna make routing harder, but maybe it's worth. And then we move this one up with the 2 millimeters. This and this. Or I mean 1 millimeter. And why is it giving me this? No, I'm gonna do. I forgot that. What key? Yeah. Okay. No. There is a way to move it with like a small pop-up. Ah, shift them. Okay. Here we go. So now it's centered again. But now what happened? The ground disappeared. Okay, never mind. Now we just extend this. Yep, and we shorten this. There we go. Okay. So now we have a decent cutout. So just to measure it again, from the center line here to the center here, we have delta y 10.6 millimeter. I'm gonna measure my cable again across like so. I have 8 it's 10.7. I guess we need even more space. And that is only for this particular cable. But I mean, if we measure from here, or actually from this line, to be honest, and down here, we have 2.3. If we take another 0.5 millimeter, that should be fine. I'm confused with Axel Stepper library. I'll just watch you instead now. I don't know what Axel Stepper library is, but yeah, welcome. So I guess we move it up 0.5 millimeter. That way we can fit the connector. So let's go 0.5 and then 0.25 on the lines. Yeah, there we go. So this one and this one, do 0.25, and this one too. Oops. It's an Arduino library to work with steppers. Ah, okay. There we go. There we go. And there we go. Okay. So yeah, this is as good as it gets. So now we have a decently wide. It doesn't look centered. Didn't I do everything properly? I probably did not. I guess I have to move it down a little bit. Otherwise it won't be centered. Ah, damn it. So how do I actually find the middle point of this? So one way to do that is, oh, sorry. I thought I had it on this mode with the camera and desk, but yeah, good that you wrote. Yeah, it's a bad habit. So yeah, so what I just did was that I increased this gap, and yeah, it's not centered anymore. So this one should move down a little bit. But the question is just, did I mess it up so much that I, yeah, there we go. So yeah, so I guess this pink line is the actual middle point. So by pressing space, I set like a delta anchor. So I'm not sure if you can see it. No, you cannot. But in the bottom of the screen, I have this, yeah, I can see I can measure stuff. Have you learned PCB design in university? No, I just did it myself. Just downloaded KiCad and yeah, played around. It's quite fun. Actually, this is a good one. So here, you can use this as a reference. So the problem with this whole PCB design is that the center points and the anchor points, the grid and everything is kind of messed up. Yeah, and then I have just built upon it. So yeah, it is what it is. But normally I try to be really careful with the what's it called again? With the grid, so that things are laid out properly, and you have like a grid where everything follows nicely. But that is not the case on this design, unfortunately. But yeah, here we have 5.3, and on the bottom side we have 5.54. Okay, so I'm just gonna, oops. That is one number, and the other number was 5. Okay, so I'm just gonna do like this in order to, oh no, that is unaligned as well. Okay, so I'm gonna do like this. Now it should be centered, unless my math was upside down. So let's measure. Here we have 4250 and 4250. Okay, so now it's perfectly centered. So the gap is perfectly in center with the USB connector. We're practically destroying one of the latches of the shell with cutout for micro USB. I mean, if we look at the camera again, so this is, yeah, this is how it looks. But the cutout doesn't really, I mean, cutting it out doesn't really, yeah, okay, I see what you mean now. So you're referring to this thing, right? This, which hooks into not really sure on this side. No, actually, it's kind of funny. I don't know if it's like a bug, but do you attend uni in electronics maybe? No, I actually didn't study that much. I just been working as software developer and doing fun stuff after work. But yeah, that's actually true. I mean, there's so much stuff on the internet, and there are friendly people who can help you to learn stuff like outside of university. But yeah, I mean, I am by no means a mechanical engineer, and I have no idea what I'm doing with this stuff. But like looking at this latch, see if the focus works this time. Come on. Yeah, anyway, even without focus, you can sort of get a sort of idea of what it is. It looks like a latch, but on the mating side, like there's basically nothing. There's nothing that latches into it. So yeah, I think it will be okay. And to be completely honest, I think this is already like way nicer than I would expect from like a quick and dirty DIY version. So I'm honestly pretty happy with this. This is good enough. We cannot really get it much better. At least I cannot figure out how to do it better. Now we just need to center this pad again. It's a little bit hard to see in this mode. There we go. Okay. So yeah, I mean that's good enough, I would say. So then we need to move this one down again. Yeah, now this is a little bit annoying. We could put it here, to be honest. But yeah, it's not good to have it there either. So this one is the Raspberry Pi Pico has an LED here, which exposes an extra GPIO. And that extra GPIO is kind of nice to have. But you know, it doesn't really matter. I don't know. Should just be close enough. Now that it's just like, it looks like an extra pin, basically. And it will follow the 0.1 inch spacing. So, in my opinion, good enough. You can just, like so. Now it's connected. Everyone is happy. If you manage to solder underside test point, this extra pin is not needed actually. Let me think. You mean if you manage to solder this? Yeah. True. This is optional, but it's also kind of free to put it there. Like, yeah, maybe the PCB house will be a little bit like, do we have to drill over here? But it should be fine. GLC PCB are usually not really that cranky. You can do some pretty crazy designs and they will just, yeah, we'll try. So I think this will be good enough. So the idea is to put like a wire from this point or this point to this, and that now that distance is way shorter. So this is actually pretty nice. So guess we can move this down. Okay, so were we happy with everything else? This one we should move somewhere here. I guess we can actually sort of put it as high up as possible and as far to the left as possible, like so. And then we put the silk screen, like we said before. We label it like here, and then maybe here, I don't know. We'll figure something out. Okay, power. Because that was what started all of this madness. I'm kind of annoyed at this line not being straight, but it is what it is. It's good enough. Shouldn't care about that. So this is VBus, right? And this is the other one. So this is way nicer. And we can try to not use that much PCB space for it by doing like this. We could move it a little bit up so that we get more area here to route. So it's a balance because we also want area there. So, but anyway, this is probably good enough. And here it doesn't really matter. We can just have some extra space. Okay. What happened here? Okay, so let's begin the routing. Oh, this will be hell to route. Let me just fan that out first. Hello. Yeah, it's already getting a bit cramped. We can route on this side as well. It's actually not that bad. Not that bad, to be honest. Yeah, I'm okay with this. And then here we have some more stuff. Okay, cool. Yeah. Okay, so I guess we should start with the hardest one all the way up here and sort of find a way down. I guess we can honestly try to route as much as possible on the other side, because then we can route it really well. Okay. Oh, wrong side. But yeah, okay. So far, it's actually pretty easy. But that will soon change, I'm sure. Okay. I need to take a really quick break. I just need to take out my contacts. 1 second. All right, back to the routing. Sorry for not talking much, just in focus mode when routing. Hope you didn't forget to turn on the mic now. No, sorry. I was just literally being silent. Oh, I hate when this happens. Is that i3 gap? No, it's ordinary i3. But it has been giving me some headache. But it's okay. I've been living with it for years. I like it, but it has its issues too. Okay, how do I route this? I kind of want to avoid having too many vias in the same area. Okay. Let's move this here, I guess. No, there. Can I get there? Oh, how do we get there? Now the routing is getting a little bit complicated. We could do something smarter with this one. Actually, we have a lot of space here, so we can just put it here-ish. Yeah, and then somehow I just recently switched to Arch Linux and I'm currently running KDE, but i3 and the whole tiling window managers seem super cool. I mean, it is really nice. I love it. Oh shit. Yeah, I kind of like it. Because you can like tile and move windows around, make them floating if you want. But yeah, I have some issues that I haven't really bothered fixing with redrawing. It is what it is. So I just gotta figure out how to route this in a sane way. So I mean, I could switch layers. So yeah, the net I'm currently working with is this one. And yeah, I need to cross this, which is kind of hard to do without having tons of vias. And I kind of want to avoid that. I mean, I could do like something, but I'm gonna have to route all of these things here too. So this is gonna be a nightmare later on. So currently I've routed all of these on the backside. And I kind of want to avoid doing like nasty routing with tons of vias and so on, which, I mean, if it works, it works, but it also feels bad. Come on. Why don't they connect better? There we go. Is there a way to test the PCBs you design in software and spot errors? Yeah, it's called the design rule check, this one. So right now, I have 39 bugs, and it will complain like, oh my god, this is too close, this is not connected, and so on. So it's really useful. But, you know, signal integrity issues, like, oh, if you have a 100 megahertz signal here, this is gonna cause issues on this other thing. That is possible to test, but it's a line of work, essentially. It is very difficult, but possible. You can simulate the circuits. So let's figure out how do we go from here to here without, I mean, we can create a bridgey thing here. Let's just do that. But we don't have design flaws anyways. Who needs tests? Yeah. You can set up rules and tolerances for particular projects, like requirements of particular fab. Yep, that is correct. And I've chosen very restrictive rules, like so that I can produce this PCB at the sort of cheap PCB houses, which don't have the highest quality, because then you can usually get away with cheaper prices and so on. A fab is a factory that actually physically makes the PCBs. Kind of curious why it's called fab. In Swedish, factory is called fabrik, with fab in the beginning. Fabricates, I see. That makes sense. Should just delete those. Okay. In Germany, it's Fabrik. Yeah, Fabrik. Yeah. Eine Fabrik. So I guess I'm gonna just have to bite the bullet here. Just have to do this nasty thing here. Really don't want to do that, but I don't see another way. It is what it is. So let's continue. Yeah, let's just continue the same fan out structure. I guess I can. So we have the ground pad. Okay. Yeah. Let's go here. All right. Oh, now we have to go here. So I guess we have to do something similar again. Okay. Once everything is connected, we can sort of space it out more and put the ground vias and stuff like that. But we need to sort of connect everything together first. So it's gonna look a little bit nasty, but it is a stepping stone. Thanks for the follow. Yeah, this is... Oh, okay. I see what I have to do. We're gonna move this down a bit. And we have to move this down a bit. And then we can do this and this. Yeah, beautiful. Now this one has to go over there. Okay. So this is going to be fun. How do we do that? Yikes. Okay. A tip about Mouser. Usually, if you buy stuff for 50 euros or more, you get free shipping. So there's always a good excuse to buy more stuff. You know, just fill your basket up to 50 euros, buy all the things. Where was I? Wait. That's weird. Yeah, in Sweden at least, or for Swedish addresses, it's no problem to order from AliExpress. They these days they also have the VAT thingy, where you pay your country's VAT when placing the order. So when the package, at least in Sweden, arrives, the VAT has already been paid, and you will not get like a extra fee for handling and paying VAT. Like previously, at least in Sweden, let's say you buy something for 100 euros, then when it arrives, you will get, you have to pay 25 extra euros for the VAT, and then like 10 euros for a handling fee. Thanks for the follow. But with nowadays, AliExpress supports the DDP thing, I think it's called, but it's that you pay for the customs and VAT when placing the order. So it's actually really convenient. As for the quality of stuff on AliExpress, that's up to you to decide. But it's cheap. Okay. All right. This is getting. We're almost 50% routed, which is kind of nice. And we haven't touched the top layer. Maybe we should do that. I don't know. So where do we want to go from here? Down there. So yeah, maybe it's a better idea to go on the top layer. So we can just, oh, that was too far. So maybe here. It's not too bad, to be honest. Could be worse. If you route all the horizontal nets on the back closer to the edge connectors, you may be able to put the vias below the thick net but above the edge connector and the other net. Let me think. All the horizontal nets. Or do you mean vertical nets? Or I'm not really sure I follow. Closer to the edge connector. Okay, you mean that I put it down like this? But yeah, I mean, as a first step, I just want to sort of connect everything together, so everything is connected, and then we can sort of optimize the whole routing. But yeah, I just want to have some breathing room, and I think, yeah, we can make this way nicer later on. But it's always, at least for me, nice to not have the rat's nest, to have everything connected first, because that gives me sort of a peace of mind. It's a little bit stressful with all of these white lines everywhere. It means that you're not done. Okay, so I'm gonna put this, I guess, for now, just like this, and all right. I think I have to start learning C++. I know C fairly well, but all the Arduino stuff is C++. Yeah, that's kind of interesting that it is. Just go with C. A lot of libraries are object-oriented. Yeah. I mean, it really doesn't hurt to learn C++, but I'm kind of conflicted about using C++. I don't know. It is really choose your poison. It doesn't matter. It's just a language. But it's easy to fall into like a bloat trap with C++. But yeah, I'm not gonna judge. It is to each their own. Okay, so now the interesting part comes. So I've already sort of wasted all of this space, and I need to route all of this crap. So that's no good. Can we do this better? And also these signals are going to be nasty. So I kind of regret doing this on a 2-layer board now. I just thought that it was going to be a little bit simpler. But yeah. It looks like there's so much space, but this kind of makes everything a little bit hard. Yeah, okay. So here's the 3. Oh, scheiße. Why didn't I connect this? Man. How did I miss that? Right, because this is the 3.3 volt output, but who's actually using that? That's only for the project area. Remind me why we scratched middle Pico design again. Well, you know why. We have this area here. Yeah. You know, I'm gonna do a nasty thing, but yeah, judge me if you want. But I'm gonna do it anyway. So just gonna do it like this. And I'm gonna do it like this. To be honest, it doesn't have to be that far up. I'm gonna move everything here down slightly. Sorry. All right. Because there's no real reason for this to be this far up. I'm just gonna move it down like 1 millimeter or something. Maybe even 5 millimeters. So why not? Really don't have to be that far up. Which is a non-issue because shell has plenty of space in the upper portion. You're right, but now I'm too far gone. I have to do this now. There we go. Wow. It is within the design rules, so should be fine. Okay, let's continue. So Damn it. I really I haven't done 2-layer boards in such long time. I forgot that these problems exist. I've forgotten how hard it is. Yeah, let's make some space here. First of all, yeah, let's just make some space. Move everything up a bit. And you're now struggling to route because project area turned 90 degrees because silk screen. Well, no, not really silk screen. It was, or yeah, okay, you're right. You're right. But silk screen is important. It is. It is. A little bit at least. But I mean, why are we here? Just to suffer, right? So let's just clean this up a little bit. Guess we can move this up here a bit. And then we can move this up quite a fair bit. We can move this, we can move this, we can move that. Right. And now suddenly we have a lot of space. So next one. You know, now that I look at it with new fresh eyes, I think yeah, it would probably make more sense to route this here. This, by the way, what I'm doing right now, that is sort of a newish feature in KiCad, that this actually works. Like previously, this would just end up in a horrible mess. But this actually works now, so that's cool. So now suddenly we have like more space, and we don't have to feel as constrained as before. Okay. All right, I should probably route this as low as possible so I can route the other nets later on. Okay, so that one goes there. This one, oh, that's just the next one. Cool. So it would have been nice to sort of just route this out here, but I can't. Wait a second. And I could move this over here. Greatest challenge of this project for me is not to end up buying an N64. But that's fine. I mean, yeah. I mean, there's a lot of interesting challenges with the project, even if you don't have the hardware. like the whole, I don't know, but of course it makes it less interesting, of course, if you don't have it. Okay. Right. And I lost my train of thought here, what I was trying to do. But at least I cleaned up a little bit, so I have more space here. So, right. I think I was trying to do something like this. Oh, that's impossible to do, of course. But I can move this one. Yeah. This is what I was trying to do. Here we go. And now I can route this easy. Except it's not easy, but easier. There we go. Perfect. Then this one, go there. This one, no. I think I should finish up this, finish up the bus first. Oh, why did we use this? Okay, I'm gonna route this horribly, and you're not allowed to judge me. There we go. Perfect. Okay. So, yeah, maybe we can do some creative routing with this. Because, yeah, why not? Yeah, okay, so we still need to route the actual reset signals and stuff. Okay. Let's just focus on all the important signals. Yeah. So I'm not judging, but you've almost made me spill my drink. Almost. Oh, sorry. I mean, yeah, sorry if I'm misunderstanding you. Sometimes, like, you write exactly what I should do and I still don't get it. Sorry about that. But sometimes it's just hard to have focus when streaming. Like, it's like the brain goes into a different, I don't know. Like, I feel like my brain capacity goes down with like 20%. And like simple things become hard and stuff. Yeah, we still need to route these signals. But I mean, seriously, if you just look at this, we're almost done. But of course, it's the last 10% that is always more work. But yeah. So can we compact this a bit? Yeah, no problem. I mean, I'm always a little bit more constraining myself than the design rules for some reason. I mean, the design rules are design rules, so it should be fine. But it's like it doesn't feel right when you're pushing the limits too far. Like doing like this should be fine. And pushing these down is fine. It's totally normal. Streaming and concentrating on task at hand is hard. Yeah, and also, I mean, I try to talk not to make it boring, but sometimes talking makes me more stupid. So now we got a lot of free space here. Perfect. So we need this net, and that is on the other side. Yeah, okay. So can we squeeze through here? Yeah, I think so. So I'm gonna open up a gap here. So we can squeeze through here. Bam, done. And this one, yeah. Let's see which side that is going to. Okay, it's going to the top side. Right. So that is going to be a little bit more complicated. So I guess what we can do is something like this. And then we put a VI here. And we put a VI here as well. And bam, done. But now this is a little bit annoying, so could move it down a bit. And it's getting better with practice. Yeah, the thing is, I'm really out of shape. I haven't done a PCB in a really long time. So, and yeah, you've heard me complain, but yeah, KiCad 6 is different in a lot of subtle ways, which make me kind of slow. Because they changed all of the icons and the way you interact with the program. Like previously, you just had to hover above something and press a key, but now you have to like click it first and stuff like that. It's a little bit different. Let's just say it that way. Okay. How do we connect this net? Do you see a path? Kind of want to open up this area, push this up a bit. So move this a bit, and then we can sort of push this up a bit. I think it's different for the better. Many improvements. Yeah. Don't get me wrong. I'm just, you know, old and grumpy. I'm just used, like my muscle memory is wrong. and it's definitely better. Definitely. Like the whole, yeah. Good thing I put off learning the software properly, so there's less to relearn. Oh yeah, good point. I remember old KiCad comparing to PCAD. It was a pain to use. Okay, I started using KiCad 4, which at the time, like 2000, I don't know, 15, was kind of buggy. Like it crashed a lot and so on. And it has improved immensely. Like it's really, really nice. And yeah, it's really, really nice. Right, I was gonna move this up. Yeah, I mean, KiCad, I love it. I'm just not really used to this latest iteration. What did I think here? I really want to go this path. Kind of feels, I mean, it's okay. Could be worse. It seems so hard compared to Eagle. Oh, do you mean, does it look hard or does it seem hard to learn? Like, does it look difficult? Like, you really have to spend some time to learn the hotkeys, because that makes you like 10 times faster in the program. To learn, it seems like there's a lot more steps to import components and things. I agree. I totally agree. And it was even worse before. Now it's better. But yeah, I agree with JTH. But if you prefer to use Eagle, then yeah, I mean, do that. Do whatever works for you. Okay, this is dead Y. Well, there is KiCad. This is not fun. Ooh. Okay, so how do we get this right? Should I try to optimize this? Pack everything together a bit. Reduce the vias. That's not fun. No. Yeah, imagine an outer router that actually works. That would be cool. So right now my brain is a little bit fried and I'm not really seeing the obvious paths anymore. Like this, we need to get there. This one, we need to get to there. That's actually, is that actually everything? That is done. That is not done, right? Need to fix this one somehow. I guess we can squeeze it in between here, to be honest. So let's just try that. Yeah. So something like this. And then, yeah, we open up this space and we make a via here. Yeah, might work. Now it's online only and subscription only. Oh god. Yeah. We use Altium at work, and yeah, those licenses are insane as well. Oh, so that one is not routed. Bundled with Fusion 360 to boot. Oh, okay. Guess that's fun. Okay, so I have a little bit of a problem. I think this net is not routed to the pad. No, right. So how do we do that? We go under everything. Okay. Time to squeeze stuff up. Is that top part gonna be a ROM socket? Let's just look at the 3D. Maybe it makes things more clear. So this, if you're referring to this part, this is gonna be like a user area with the power and ground. And then here are the some special signals from the bus, like interrupt pin and so on. And this is the extract GPIOs from the Raspberry Pi Pico. So the idea is that you sort of solder wires from, I don't know, you can put headers here as well, and then you can solder like whatever you want here, perhaps like a MOSFET or LED or display or, you know, fun stuff. It's the user area, so you can do whatever you want here. It's for experimentation. But, I mean, honestly, it's not even 1 a.m. and we're almost done. I'm kind of impressed that we managed to get here. So the right signal. Okay. We can, no, we couldn't. Only 2 signals left. That went better than I thought. So is it this one? Yeah, okay. Those signals are really important, and oh my god, what a mess. Oi, oi, oi. Compute muscle, let's go. Yeah. Okay, should I pack this together a bit more? I think that might be a good idea. And then we can move this stuff further up. Oh shit, this is where the power stuff is. Right. But I kind of want to move that. No, impossible. Okay. Okay. It'll suck too much power from the N64, possibly frame something along the way. Yes, I made a power budget. I don't know if you saw that. Let's just look at it. No. There. Here. So this is by no means correct, but it is you know, what do you call it in English? Between the thumb and the middle, or between the thumb and index finger, you know? Just sort of eye measure. It's something, but it's not correct. But it's at least a rule of thumb. Yeah, something like that. But more like it's a guess, but it's not completely out of the thin air. It's just, you know, I've looked at some data sheets and so on, but they specify ranges and are, yeah, ballpark estimation. Exactly. Thank you. And yeah, but this is for like the final thing. So yeah, for the basic one, we only need one RP2040. But it's actually the Pico board, and yeah, it draws around 100 milliamps at most. And I don't remember if that is on a 5 volt or 3.3 volt, which makes quite a big change. But yeah, the ESP32, it's really power hungry. And SD cards use more power than I thought. I didn't know they were that hungry. But it kind of makes sense though. Okay. So going back to this one, we still have these 2 signals, but we are getting there. So we kind of have to route them this way. We could also, oh, this is kind of nasty, but we could also, no, we can't. Or we could actually. But I don't like this. But we might have to do this. Like so. Wait. But that is connected. Ah, right. Oy. Yeah. This is not good. This is not good at all. Need to figure something out here. So, I mean, I could also just do something really nasty, like so. And then sort of route the signals. Now we have to cross this huge barrier, which only is possible on the top layer. Ooh. I mean, technically we don't really need this, but you should connect them together. Why are there 2 VCC pins? There are actually 4 VCC pins. So on the top layer, we have this one, and we have this one. And on the bottom layer, we have this one and this one. And they're all the same net. And it's good practice to connect them together so that you have a stable, good, solid power supply net. But now that I look at it, we don't really need this little thing. It's enough to have the vias to the other side, like so. Can we do something smarter? I mean, we want the right signal to go here. So actually, right. Maybe I'm just thinking too much. No, it is the ALH. So I could actually do something like this. And then I get the signal here. And then here we put a via. And wait. Oof. We're gonna need to split this one up with a via. No good. No. It's funny, we have literally 2 signals left. This is gonna be, yeah, there is an obvious path, I'm sure. I just don't see it. Yeah, this red path here is annoying. Maybe we can move it over here and put it on the other side. So instead of doing like this, just put this on the other side. And now we have freed up that part. I had prioritized high frequency signals like ADH and L, routing them first as clean as possible. Yeah. In a way, LH and L are actually not high frequency. Because they're just important, but because 230 nanoseconds, that is not super fast. Read, on the other hand, is going to be a fast one. So how bad did we route that one? It has 1, 2, 3, 4 vias. Same with write. That has only 2 vias. But I know these signals are important, but they are not super fast. Like this is basically 10 megahertz. And this is basically 20, I guess. They need to be clean and sharp. Yeah, you're right. We want the rise time to be short. Same goes with the whole bus. I mean, all of the signals are important, like the data pins. If they are not good, then you get crap. So I don't know. Maybe this board will suck a lot. So, and also not having a ground plane is gonna suck a lot as well. Like it's really not good. But we could always add, like we're making a 4-layer variant. So for those who want this board in a 2-layer variant or 4-layer variant, you can do that. Yeah, it worked with jumper wise. You're right. You're correct. You're you're right, Luke. And thanks for dropping by. Yeah. Yeah. By the way, I was made aware of the fact that you can use the USB data pins as GPIOs. That was really cool. That was, so we were discussing different ways of, you know, using 2 Picos and stuff. We are not gonna use it, but it's an interesting fact. N64 blaster, what is that? Yes, no PIO on USB though. No, you're right, you're right. But for like chip select or something, I don't know. I have to look at this. Ooh, that's some routing, yeah. Yeah, no, so I'm not really proud of this routing, but it is it is what it is. And we have 2 signals left to route, and they're kind of important as well. So, so what do we do about that? We want. Right, now I remember what I wanted to do. So I wanted to move this up to the top layer and then make a via here. There we go. And once everything is connected, I will try to add some air around the all of the signals and put some ground vias and stuff like that. But yeah. I guess that it is cheaper than using flash memory. They're flash as well. Battery-backed SRAM feels very old school. I mean, to be honest, yeah, true. We could save it down to flash and so on. So yeah, you're right. But it could also be for the RTC to keep time. But with the Wi-Fi module, you don't really need that. Okay. Okay, everything is routed now technically, but you know, we need to clean it up and try to add space, not have yeah, it's actually 0. Everything is routed now, but it looks like crap. It's still it's 1 a.m. 1:05. It's not too late. This part I'm pretty happy with. This part is I don't know, it's not bad. But this, yeah, so let's I have a few goals. There should be like around the signals we want to have a ground via in between whenever possible, so we get some at least decent signals. I mean, it will not be perfect, but yeah. So perhaps here we can move it down quite a lot, and like so. Now we have some more space. I know that you're not really supposed to make like arrays of vias, but still, yeah. Then we can add like ground vias between the tracks and stuff like that. So it's kind of nice. So this is a little bit congested. I'm gonna try to free that up a bit. Having like tight buses looks cool, but it's actually really bad if you don't have a ground plane below. So we're gonna free up some space here. And then the reason why you get like a hole here is because there is no direct connection to ground. So that's why you should add stitching vias to ground a little bit here and there. It's always good practice. We're gonna add a lot of stitching vias later on. But yeah, just to, yeah. This stuff is a little bit icky. These signals are really close. And yeah, I'm not really sure how to solve this in a nice way. Maybe it's, I mean, it will be fine, I'm sure. But it's still kind of nice if we can clean it up a bit, make some space. Oh, it doesn't go anywhere. There we go. Actually, we want that here. It's already starting to look a lot better, I think. But this area we need to sort of, I want to have some space here. I'm not really sure how to solve that. And here, close to the power stuff, it is kind of icky. So now I want to sort of widen this gap somehow. Oh, what happened here? Okay, so in order to free up this area, we need to sort of push everything up a bit. So this one we can actually push up quite a lot, which results in everything sort of moving up. So that's good. So now we can move these up without any issue. There we go. Now we can move this up. So now suddenly we have a lot of space. So we can add some air around the signals, or rather ground. Now we have a problem here, because the goal is to push this up a bit. So we can already push like this one up a little bit, and this one, but we're not really there yet. You see a lot more space between the signals, which I don't know if it technically makes any difference, but kind of feels better from a signal integrity point of view. And then we can put some ground. I'm itching to redo this from scratch. Yeah, I see, I get it, but yeah, I don't know. All right, we wanted to add some more stuff here. So actually these can be closer together, and then we can move it up a little bit. Yeah, I guess this is it. So we can add some stitching vias everywhere to make the signal integrity better and the ground plane more happy. So is there anything obvious we should fix? Like the distance from here to here is let's see here, from here to here is 0.75 millimeters, which is a little bit too narrow. Should do like this instead. Yeah. Now it's 1 millimeter, which is the official guideline, which actually goes from the edge. But yeah, I think this is good. Now we also get some ground here on the edge, so that's fine. So all right, we have the same constraint here actually. Here's only 0.5 millimeter, which is a little bit narrow. What if you line Q1 with VCC on pad 34? Right, so you mean if I move this all the way, wait, what did you say, by 34? Oh, you mean I put it here? Oh, here's actually a lot of space. Yeah, but then I need to reroute this. I mean, you're right. It was a bad choice of me to choose this instead of this. Now in hindsight, it would have made so much more sense to put it here. You're totally right. But moving it here forces me to reroute this. But it might be worth it. Like, it could clean up a bit. So let's do that actually. So I'm gonna just remove this part of the signal and keep the rest routed. So we remove that. And then we move this and this. I guess I guess we can put it here or something. So just want it to be centered. Yeah, there we go. And then we put it like in the bottom, like so. Stay first. Yeah, I did. But I'll power through this. It will be fine. Then this one, it's just resistor. Yeah. Right, this is nothing important. Just a gate drain resistor. Okay, and then we take this and move it over here, and we take this and move it and then we need to fix this one. But now maybe we can do something smarter, way better. We can move this down quite a bit actually. So then we can right, this is what I thought. I wanted to move those down and move this one up here, and then this one just oop. Remove this a little bit. So yeah, much better. And then we can also open up some space here. So yeah, thanks for the suggestion. It was really good. So now I think, do we have any VS that are not needed anymore? I guess technically this one can probably be done completely on the top layer. So we can do like so, and then we can get rid of that via, because VS are, you don't want to have too many VS on a single path. If you can avoid VS, that's good. So that's nice. Yeah. So if we run the DRC now, let's see, do we still pass? We have 6 errors. Okay, I don't care about the silk screen overlapping and stuff like that. Oh, this one is a little bit scary. No zone. Okay, I guess it's the ground layer that gets messed up because of the, since we went from a 2-layer or 4-layer to 2-layer. Let's see here. Right. Yeah, we don't need that because everything is sort of, or actually, let me just see. Right, we still want the exposed copper here. We can move the silk screen. There you go, happy. It's complaining here, okay. Don't need that to be that long. Because now the routing to the power goes here. Yep. So courtyard overlap means that I've placed one component on top of another, which is actually fine in this case because we are doing some non-standard stuff. So that is okay. Same with that one, that's also okay. Arc on edge cut. Board has malformed outline. So that is really weird because these are definitely closed. I mean, they're supposed to be closed. Okay, let's fix these then. This could be some KiCad migration thing that doesn't. Yeah, okay, now everything is fixed. So okay, so we have the courtyard overlap here and here, which doesn't matter. So now we can look at the warnings. We have some silk screen overlap, which yeah, it's a bit annoying, of course. Can move that down here. Yeah, that doesn't matter. Yeah, that happens. Now this is a really important warning. Why is this only a warning? We have a track has unconnected end, and if I zoom in, I see that I left some junk here. This could be potentially bad, but in this case it would probably be fine, but still nasty stuff. You don't want that kind of junk left. And then here we have we have some bad tracks. So let's just redraw this track. So for some reason it got sort of one of those weird half tracks. Okay, better. Okay, so now all the warnings, it's just silk screen, clip a solder mask, and footprint overlap, which is fine. So yeah, now we're ready to actually finish up the board by doing some silk screen, and we can actually send this off to the fab. But yeah, first we're gonna do some ground vias, I guess. Let's just find a decent grid. Yeah, this is probably fine. So yeah, I don't know. I'm just gonna put some ground vias a little bit here and there. Oh, thanks for the sub. All right. So what I'm doing right now is to add some stitching vias to ground and try to improve the signal integrity of this board. Yeah, it's always good with some extra ground. All right, awesome. I believe you're the very first one to sub, so yeah, welcome. Congratulations. So yeah, what we've been doing, I don't know how long you've been here, but we're just sort of wrapping up a DIY variant, which is supposed to be like extremely cheap and easy to build yourself. So it's literally a Pico, $4, and a Breakout board, a tiny chip here, a MOSFET, which is like very cheap. That's all the hardware you need. And then we get some project area here where you can solder your own stuff. And the limitation is, of course, the flash size, which is very small. It's 2 megabyte, but it's enough to run your own homebrew. So this is like, yeah, the bare minimum for a homebrew. And the board is 2 layers, so it's very cheap to produce. It's like $2 for 10 of them. So yeah, that's about it. And right now I kind of wrapped up the signals, and we're adding some stitching vias to ground. We're gonna add some select screen to explain what these different pins do. And then we're done. I always thought N64 IO was too fast for microcontrollers. Yep, that's right. But the Raspberry Pi Pico is special. It has the PIO, which makes this possible. So I can just give you a quick overview of the code. Yep. Nice job. Really looking forward to going back and following your PIO work. All right. Yeah, so the purpose of the stream was actually to implement stuff with PIO, but we got sidetracked and ended up doing another PCB. But yeah, in short, this is the whole cart code in C. So we're really just setting up some GPIOs. We're initializing PIO. We're starting the CIC chip on the second core. We're waiting for a reset. And then we have this loop, which waits for an address. Once we get an address, we save the address. But if the address is 0, that means that we should fetch data. So we look at the address and look if it's the very first word. In that case, we can inject a different one. So this is a way to change the bus speed. So we can run it at a much slower speed. Later on, we're going to make this faster, but for now, we can kind of run it slowly. And if it's another address, right. So if it's another address, we load it from the flash. And then we increase the address as well, so that if you have multiple reads after each other, we are increasing the address. And that is the C code part. So the PIO part is this other file with, this is all of the code. So just to go through this kind of quickly, we are implementing the protocol more or less according to the signals ALI-L, ALI-H read, and then the AD. So when basically when this happens, you should latch the address, and then when the read goes low, you should prepare data, and when it goes high, it should stay stable, and when it goes low again, you should read the next 16 bits. And that is exactly what we do here, but implemented in PIO. So yeah, there you have it. So going back to the PCB, I'm gonna, wow, it's already 1:43. So it took like 45 minutes just to add some final touches to the PCB. Everything always takes more time than you expect. But yeah, so this PCB is not going to be like a perfect, fantastic, wonderful PCB. It's 2-layer, cheap, but very accessible and affordable board. And yeah, it shouldn't have issues. Like, it shouldn't be bad. It's just not perfect, if that makes sense. Because it's 2 layers. So yeah, I added a bunch of stitching vias to connect together the backside and front side ground layers. And now I think we're done with that. It's good enough, I would say. We could add some here too, I guess. I think this is pretty decent now. So let's add some silk screen. So let's just remove the GRC markers. it complains about the small overlapping areas and stuff like that. So yep, all of that is fine. So we can remove them as well. Bloop. So the question is, what is a good way to present these IO pin labels in? So I was thinking of having them horizontally like this, but they're actually going to be about these pins. So Pico is really a game changer. What amazes me, it is out for more than a year and yet still not recognized for its power. But we're getting there. We're getting there. And I think, yeah, for each project that pops up, that does something interesting, it just, yeah, proves that it's pretty cool. Cool. Okay, so oops. So I'm gonna need some help from you, chat. Ooh, how should I present these IO as labels on the cell screen? So I'm thinking I could go from 1 to 8 from top to bottom. So this is pin 1, and then have a some sort of graphic mark, like I don't know, something that like I don't know. No matter what I do, it's just gonna end up being not so nice. But I mean, I could do like, why is it being weird, man? Here we go. So this, nobody will understand this. It should be easy to understand. And this will be really convoluted and look really sort of not nice. So I don't know really, how do you usually do this? I could also make a number, you know. I think I'll do that, to be honest. Just write 1. Put it here. And then we can have numbers here, and there will be no ambiguity. I think you can just put the same order starting at pin 1. Yeah, okay. So I've marked a 1 here, because some people might not understand that this is pin 1, especially, you know, with enthusiasts who might not be, you know, that yeah, who don't really are into electronics normally. So let me, thanks for the follow. So I'm gonna, yeah, simply just map these. So let's just do like this. Oh, I missed one. Okay, I think I got it right now. So I mean, everybody should be able to understand this. This is understandable, right? A little bit closer. And then here, I guess I can do the same, but I can call it ABCD, perhaps. I don't know. You can also put a PCB picture in the repo explaining. Yeah, definitely. But sometimes, you know, you have the hardware in your hand and you just want to understand. You have it in your hand and you just, okay, here, without having to look anything up on the internet. So, yeah, in order to not confuse people too much, I guess I'm gonna call this ABCD. Wait, is my grid? It should be right. Center. Ah. So wait a minute. This is not aligned. Okay. Let's fix that, because that's gonna annoy people. I'm sure. So we want it to be aligned with this. Wait, what just happened? There we go. Okay. Okay, so what do you think about this? Does it make sense? So you have this here. I should have ground and power here as well. Yep. Because this is ground and this is VCC, and it doesn't say that anywhere. So that is bad. Let's fix that. I guess actually write it like this, or maybe people will understand this the best. And adjust it to right. Damn it, it's a bit too wide. Thanks for the follow. Yeah, there is actually no reason for it to be this far to the left. I could have moved it to the right, but now there's so much routed, so I don't really feel like moving everything to the right. But damn it, I guess I should. I really feel like wrapping this up now. Thanks for the follow. I don't know really. How do you do this in a nice way? Nah, okay. Because if I do like this, will people understand that it's the whole column? And people might get confused about this pin and this pin, which is which. Like, yeah, I don't know. That doesn't really look good. Should I make like a bounding box around it perhaps? Put a rectangle like so. What if you place a filled shape? Yeah, thanks. That is exactly what I thought about doing. So something like this. And let's just make sure it's symmetrical. Is it? Looks kind of off. Doesn't it? Can we get it to align? I'm just gonna change the origin. I just forgot how to do that. There's a button to do that. Reset origin Z. Okay. Or guess it's the other one. Yes. Okay. No, I don't get it. I want to set the origin, but I don't understand how to do it. It's not like perfectly centered. I think. No. There it is. Okay. So I don't know. I'm kind of getting annoyed at the KiCad now. So I'm trying to. It's a little bit annoying to watch, I guess. But the thing is, this whole project is kind of messed up with the grid layout. And I want to place no, not for drill files. I forgot how to do this. Yeah. The grid origin is the sort of where the grid starts. And you're supposed to be able to do that by pressing S, and you can reset it by pressing Z. So if I press Z, it's reset, yeah. But if I press, okay, so that is how you do it. Okay. So I just need a good thing to click on. So I want this place, but I can't click it. Very annoying. There we go, finally. So now everything is aligned. Oh, thank goodness. So, but now I see that these two things are actually not perfectly aligned. So let's fix that. That is actually easy to do and not too annoying to observe, I guess. Let's just fix that really quickly. yeah, so we want this to be like a perfect grid like this. So I'm just gonna move it down a little bit first. We can see, there we go. Bam. Now it's fixed. Now it feels better. We can redraw this. There we go. And then we can ensure that this is actually on the same grid, and it kinda is. Okay, just double checking, we can see that everything is on our grid now. Yeah, so the thing with having stuff on a perfect grid is not just for looks, it's that you can put like jumpers and boards and so on. It is actually kind of nice to have them aligned. Now that I look at it, I kind of want to move everything one step to the right, but yeah. Can do like this, but first we're gonna just make some space. Come on, snap. There we go. Wow. This is impressive. If you pay attention to what's happening here, I'm actually moving the component with all the net being connected to all of the... And again, why is it turned 90 degrees? Well, because otherwise I get this one on the wrong side. I mean... Or you mean you want this one to be turned 90 degrees? Because that is easy to do. I thought it was, you know, you want to be able to put wires between this and this easily. Maybe I'm misunderstanding here. But like if it is, let's just... Okay. Come on, KiCad. You were so good. There we go. Okay, so just so I understand you correctly, do you mean this one should be 90 degrees? Or do you mean that the signals should be 90 degrees? Like if I do it like this is no problem. This is, I mean, bam, done, no problem. Now you have, in the top you have 3.3 volt and in the bottom you have ground. This feels good, I get that. But the signals being connected over here have to pass over the 3.3 volts. Did I understand you correctly or not, JTH? Is this what you want? GPIOs on the bottom, data on top. GPIOs on the bottom, data on top. But that is how it is. But maybe it's too late. Maybe I just don't understand. Because when you have it like this, we can easily connect everything together. I don't understand. Or you mean that they should actually be in here? all lines going extra mile because at some point we wanted to make some space. Well, yeah, that's true. But like, well, I mean, from a usability point of view, I think this is okay. You get the GPIOs here, you get the signals here, you can connect them together. Right, I should make this two points wider. Logically, GPIO should be on the top or in the right 90 degrees. Okay. They go here. Sure, this is bad. But yeah, I mean, I don't know. I could make this one wider as well. But it would be nice to be able to connect all of these, I guess, to something. But practically speaking, I guess you won't have everything connected because there's only 4 GPIOs. Yeah, I think this is good enough, to be honest. So let's make that the bounding box now. So now everything snaps properly. And we can make another one here as well. Should that be on the top or bottom? Or both? So there's really no ambiguity. If you misunderstand this, then I don't know. This should move as well. And what is with pin 3 of data connector? Is it routed? I think so. Wait. Why don't I get it? Oh, it is. No? What? Where's the rat's nest? What? Oh, shit. But it's there. What? Should I press F8 one more time? What? Did I remove this by accident? What the heck? Where did this come from? Now I'm confused as heck. Is it one of these? No. What? Now I'm really confused. We have these are the CIC pins. This is the SI clock. This is the SDAT clock. I don't know. I must have gotten this from somewhere. I'm really confused now. And I've forgotten where the good sources are with the proper pinouts. So just hang on a second. I'm just gonna open up a different PCB. 1 second. So it's pin 21. Okay, so these two signals are the same. I must have used some wrong source. Yeah, again, I wasn't really sure about these signals, what they actually do. But yeah, according to what I'm looking at now, this signal doesn't exist. Or it's like the net name of this net, but it's called s.dot here. So let's remove this. This signal doesn't exist, which means that yeah, bye-bye. So let's do like this. Move everything up one step. There we go. Okay, silk screen. Yeah. Blah, blah, blah. Courtyards overlap. That's fine. And that's fine. Okay. So no errors. I want to add some ground here. Okay, I think we're done. I think, all right, we're gonna need to update the silk. Gonna have to remove this one and do. And now I remember you were saying something about pin 3 when I was writing this, and I thought I had miscalculated something here. But yeah, thanks. And I missed your suggestions again. But yeah, that happens. So does it match? S.dot, sclock, NMI, int, code reset, du, declock. Yep, matches. 5, 6, 7, 8, 5, 6, 7, 8. Perfect. Okay, I think now we're actually done. We could move the silk around a little bit, but I think this is good enough. We don't have a logo. Oh, this is not good. We have to fix that. Back silk. Actually, we can flip the board. Bloop. And yeah, where do we want it? Here, perhaps. Let's left adjust it. All right, the Pico is there. We need to change the date. I know you can script this, but I couldn't get it to work. Oh, also it's called light. So we can put it, I don't know, it's kind of messy, but I don't know. Maybe it's good enough. Put it here instead. The pad matrix shouldn't have one more pad to avoid someone connecting 3.3 volts to a signal. I don't really understand. Can you explain more? I'm a little bit. It's late and my brain is fried. Do you want to have like a space in between here, or do you want this to move one step to the right? Yeah, maybe that's move this one to the right, like so. So having it this way, the worst that you can do is to connect it to ground, which shouldn't be a problem. But adding an extra row here is kind of because of the alignment. Yeah, I agree. Let's do that. Yeah, I agree. Let's fix that. We can fix that. Bloop. And we just, oh right, it's the other way around. Actually, let's do like this instead. We move this one step, and we copy this, and we move this one step, and we drag this and this, and done. Yeah, that wasn't hard. All right, I need to press update footprint. Update footprint. What? Why doesn't it update? And what just happened here? Something weird just happened. Oh, I see what happened. Yeah. Again, I'm a little bit slow. Here we go. I've just remembered, if you can see this, your Pi Pico has been stolen. Joke. In silk screen. Ah, yeah. Yeah, who wrote that? It's here, right? Was it Stack Smashing? I mean, I've been really uncreative. Like, there's no fun silk, no funny Easter eggs or anything. It's just, bare bones on the PCBs, but you could put down a lot of fun stuff. Okay, let's move this back. Okay, of course. I guess we're gonna do like this. Okay, guess we're gonna have to route it ourselves. No. Okay, I think. All right, we need to update the silk screen. The rectangle is one off, I think. Yeah. Oh, this. Okay, so check this out. Oh no, now the one is off. And actually, I'm gonna be like extremely verbose. And just like this feature. Like previously, you could just hover something and press E. But I have to relearn. I think you have to press escape before selecting something new. I'm not sure. Okay. So now there is no ambiguity. Nobody cannot understand this. Like, everybody should be able to get it. So what do you think? Aside from the signal integrity and kind of two-layer mess, I think this is pretty neat. You don't use Control T to do erase. Well, I think those are scary to do, to be honest. Like this is a footprint, so it's one unit, one thing that I can sort of move around. I don't know. With the generator stuff, it's kind of scary. It's scary because I don't understand it. So I'm sure it's really good and useful. It's just, I think it's scary. So any more changes you want to do before we sort of commit this to the repository and people will, you know, start ordering the boards even if nobody has tested them and so on? Is there anything more we should do? Kind of want to add one more here. You don't. It's passable. Will do. But perfectionist in me screams, yeah. Inside of me too. But you know, at some point, I don't know. I don't want to. I've spent enough time. Like for me, this was like a time boxed thing. Like I wanted to finish it during the stream today. Now it doesn't have to be perfect. It has to be okay. Yeah, it is what it is. So, yep, let's save it. Okay. So, looks like this. On the other side, looks like this. The little metal thingy sticks out here, but it's still, yeah, you can plug in your USB cable there. Let's just do the ortho, yeah. So, looks nice. All right. So I guess we will we'll plot this, call this PicoCart_lite 1.0. Plot generate drill files. Just gonna press B one more time because that is the worst thing you can do. To plot without pressing B. B refills the zones. It's really important you do that. Yep, there you go. Save, close, save. All right, did I update the date on both sides? Because it's technically, okay, so no date on that side. And it says 26, it is 26 now, yes. But in the project settings, it is actually 26 now. Save, close, close. By the way, here's a Pico-shaped board with 16 megabytes. Oh. Should be able to run Mario. Oh. Oh, and it's, I guess, pin compatible, yeah. So before, since you're here, Luke, let me just open up PicoCart really quickly and just show you this power solution. So we looked at the datasheet and read it, and it seemed this seems to be the correct way to do it. But essentially, this is the N64 VCC, and this is the VBus. We want to switch between those, feed it to VSys. Yeah, I just kind of want to double check that this is good. Because I don't actually know electronics, I just try. The whole MOSFET, understanding MOSFETs and so on. Yeah. Stream is frozen for me, so can't see the thing you're pointing at. Oh shit. I took a screenshot before. Maybe that messed up everything, but OBS is actually, it's pushed to GitHub. Yes, it is. That is weird. Okay, I'm actually seeing the stream on a different window and it seems to work. Maybe if you refresh, stream's fine. Okay. Yeah, maybe if you refresh. But yeah, I'm just wondering about the power solution here, if that is good. Yeah, it's a really simple design. It's only the routing that was a drag to solve. But yeah, I think it's passable. Like you say, JTH, it is. Actually, let me move this down a little bit. Now we can align it to a grid. There we go. Oh, sorry, it's not pushed to GitHub. Sorry. I was so close to pushing it, so I thought I had done it, but it's not actually. But yeah, it was this MOSFET thingy that I was curious about. So I just wanted to have like a second opinion on this. Like, yep, that is correct. Go ahead. I mean, it should be fine. We're doing basically what it says in the datasheet. So. And then we're using this 3.3 volt out as a 3.3 volt reference for the project area. Yeah, I think it should be fine. So I will plot it again. So the idea is it's an ideal diode between N64 VSys, N64 2 VSys, unless VBus is present on the Pico. Yeah, exactly. So it's the power switcher to either you have the USB powered through the USB cable, or it's N64 powered. But it could also be connected to the N64 and you plug in the USB and it shouldn't blow up. Seems plausible, but my brain is so fried I can't say anything confidently. Okay, don't worry about it. We kind of double and triple checked this with the datasheet, and this should be fine. I added this bleed resistor for the gate to drain the gate capacitance in case, because that's sort of good practice. So that's the only change I made. So let's export the things again. Plot, generate real files. Yep. Close. Yeah, I guess. Did I get a bunch of backup files this time? No. Right. Yeah, I should probably add the license file for that one as well. Let me just find the files. Yep, and then we got this. Okay, I think this is it. But there's no harm in having the footprint. I think you could drop the VBus resistor. There's a pull down on the Pico due to VBus sense driver. Okay, but yeah, I mean, you can always DNP it, but now there's a footprint, so okay. So I guess, should I merge this back to the developer branch? Because that's where people are looking, I guess. Yeah. Done. So it was a productive stream, but we didn't really get to do what I wanted to do. Yeah. So the plan, look, today was to write PIO, SPI, QSPI stuff. We got started with it, but we got sidetracked and ended up making a PCB instead. But now we have a really, DIY friendly, super simple 2-layer board, which, it should really lower the barrier, and it can boot, simple homebrew and stuff. But yeah, like you said, if you use this one, you get more. Oh, they even have some extra button here. User, reset, boot. Interesting. So I wonder what pin the user button is connected to. Probably says here somewhere. Ah, yeah. Okay, 24. Okay. All right. Yeah. Oh, and they also pulled out 3.3 volt here. That is, honestly, for me who's using a J-Link, I kind of like this because I need the voltage reference, and there's only one 3.3 volt pin, so I had to connect that in a janky way. Because in my test setup here, I have the Pico connected to a PMOD interposer, which is connected to the PSRAM and the SLA logic. So I kind of ran out of 3.3 volt pins quickly. It's also USB-C. Ah, fancy. Yeah. Future. It also has a power LED. Interesting. Yeah, that's cool. Okay. Yeah, my brain is like extremely fried right now. It's been a very hot day today as well. And yeah, it's been a lot of fun to do PCB stuff and coding on stream. But I think I'm gonna wrap it up now. Yeah, so see you next time. And yeah, feel free to join the Discord. Maybe I should drop a link to the Discord in case people wonder. Because we have a Discord now where we can discuss. Yeah, just 1 second. Copy link. Ah, damn it. Twitter. I have to curl it. Oh god. I guess I will create a new invite. Oh shit. Yeah, there you go. All right, nice to hear, temporal user. It's always kind of hard to know who's actually enjoying the stream and so on, because it is a very niche content, and yeah, it can be, I guess, perhaps quite boring if you don't really follow what's going on. And I'm not a good entertainer and talker. I just say what I'm doing and so on. But yeah, I try to make it interesting. And if you have any suggestions and so on, just let me know. But yeah, that's it for today. So thanks again for joining, and all the suggestions and ideas and tips and whatever. It's really, really nice. So yeah, see you next time. Thanks.